Good afternoon, everyone. Welcome to the first workshop on compositional 3D vision and 3D challenge. Today we have a really exciting program. First, I would like to thank all the co-organizers, Professor Wolfgang Hedrick, Peter Vajda, Natalia Neverova, and also the workshop the challenge 3D plus challenge co-organizers, Habib Mahmoud, Mohammed, Jiang, Yuchen, and Professor Peter Bonke, and myself. The background on this topic is that interest in 3D vision and accessibility to 3D sensory input has been increasingly growing, and what we can do to accelerate research, enable more like exciting research in AI that is more useful for more people is growing, and this might excite a lot of future research that we together in this workshop we're gonna talk a little bit about it. There has been already some existing work that has facilitated that is at the intersection of 3D vision and language, including, for example, 3D visual grounding, which is a task of referring to 3D objects in 3D scenes. For example, you can imagine asking your like robot to pick up a cup on the table close to the door. You might imagine having access to something like that in the future to ask your robot to bring you a cup of water. Composition of motions. Now, these days, there's an example for that is a sync. So for the first tasks, scan, refer, and refer 3D is one of the popular examples. Another example of composition in 3D is composition of 3D human motion. And one example of that is a sync like data set by the imaging group in the École des Mondes and also other collaborators. So you can, for example, ask the AI system to generate a motion of a person sitting down while drinking from a cup. Other applications also include the recent part GLOT dataset, which has been used to which is a method that facilitates segmentation by weak supervision. So you have access to a large amount of text and corresponding 3D input, and you want the model to figure out by itself which pass of the text refers to which pass of the 3D object, in particular, in this case, 3D pass, right? So these are all of these are exciting examples that refers to that should lead to a lot of exciting research that could be that is happening in this field. And our hope from this workshop is to learn what's exciting in this field and to shed some light on the current progress, celebrate the current progress exemplified by these tasks, and also our speakers will shed light on ongoing research and exciting future directions. We have really an exciting program ahead of us. 5 talks by really excellent speakers and a challenge. So our speaker have a fantastic lineup of speakers, including Georgia Zara from Caltech, Katerina, assistant professor at CMU, Jazindra Malik, professor at UC Berkeley, Matthias Nessner, professor at Technical University of Munich, and Angel Chang, professor at Simon Fraser University. And for the challenge, the 3DCoMPaT challenge, the paper itself was initially presented as at ECCV 2022. We actually were not able to make it in person, but this is probably the first presentation of the data set. So it's a data set on compositions of 3D objects, and it has part segmentation and also as well as material segmentation that are associated for every single pass. It has about 10 million, and there will be a few minutes presentation that will be talk about the challenge later, as well as announcing the winner later on in the workshop program. We have a poster session that will happen from 3 to 3:30 p.m. and this will cover these 7 papers, and also paper spotlights. Will be having 3 presentations so far, that each one of them is about 6 minutes or so. So this is a summary so far of the workshop, the program. So we'll have the talk by Georgia and Katerina in the beginning, and then the 3DCoMPaT challenge, and Justina Malik's talk, and then we have a break. And then after the break, we have the talk by Matthias Nissner, and then poster spotlights, the talk by Angel Chang, and then after that, we have 45 minutes at the end of panel discussion. All right. While we are waiting for our first speaker, I'll be happy to answer any questions. All right. You unmute, remote participant will be able to hear.
Okay, yeah.
Okay, nice. Just will give a quick introduction.
Yes, sounds good.
You want to
Go ahead.
test the presentation?
Yeah, let me set up. How do I swap this place? You know, we swap display, yeah. And then and then I have to share here, right?
Yes, exactly. You can validate that with the online participants.
Yeah.
If you can hear you clearly.
But share. So to the Zoom people, can you see the screen of the slides and not the presenter view? We're ready.
Okay. So I'm excited to introduce our first speaker. Georgia is an assistant professor at Caltech, and prior to that, she was a research scientist at Facebook Research. Georgia obtained her PhD in electrical engineering and computer science from UC Berkeley with Sunra Malik. Prior to Berkeley, she earned her diploma from National Technical University in Athens, and she her work has gained a lot of attention and prizes, including the TPAMI Young Researcher Award, PAMI Mark Abraham Award, among many others. So with that, I would like to pass it over to you.
Thank you, and thank you for waiting. I was trying to find my way to the room. Appreciate it. Okay, so today I wanted to talk about the path towards any object reconstruction. So I have been working a lot in the field of recognition, which is the problem of taking one image, any image, and trying to understand what has happened, what that image contains. What are the objects, where they are, what is their location? You might have seen a lot of these problems, object detection, segmentation, and so forth. And this has been one of the most popular problems in computer vision, and I'm going to claim that it has been also one of the problems where we've seen a lot of great success. Perhaps in computer vision, if I was to call one problem that we have made the most progress in, I would say this is it. Object understanding, object recognition from images. And so here's the example of mask CNN. It's now at this point, it's 6 years old, where the model takes in an input image and is able to detect the objects, say what objects they are, and also localize them precisely by outlining them. And of course, now we have all of these big models, and we've seen a lot of great work, such as SAM, which takes this problem of localizing and segmenting objects and takes it to the next level by segmenting any object. You lose the ability to say what object it is, but you gain the ability of segmenting objects in an open world vocabulary setting. So you win some, you lose some. Always be critical of work. Do not believe Twitter influencers that say that everything is solved. SAM is fantastic. It solves a problem by clicking on an object. That's it. Okay. So SAM does not have the ability to say what objects we have in images, but there's this other line of work in the AI field, not in computer vision, language modeling. And there, I'm sure that you're all aware of the great and exciting progress that has been made with building large language models that can understand and answer very complicated questions. And where, in my view, a lot of magic happens when you bring vision models and language models together. And one such model is Flamingo. Are you familiar with Flamingo? Yes, vision language model. It takes an image in and you can ask questions and it answers these questions. So Flamingo builds vision capabilities, language capabilities, and fuses them together. And there's this open version of this from the layout team called Open Flamingo. And what Open Flamingo can do is like you give it the input image. This is my collaborator, there's our collaborator Sabera, and you can ask it, what is this? And it will say, a woman wearing an EEG headset. This is a fantastic result. And the reason why it's fantastic is because I know the pain of building a classifier. I know the pain of building a classifier for a new object. An EEG headset is actually a very uncommon object. And if I had to build a classifier with the old methods, I would have to go to the internet, try to source for a lot of training examples, and try to learn a new classifier, append probably those images to ImageNet, let's say, and train my classifier from scratch. And now this all seamlessly happens with language and vision understanding. So this is a very brilliant result. And with these results in mind, there's a lot of people that think that, well, I think that maybe recognition is solved. And there's a lot of people that claim that recognition is, it's done and so forth. And I want to show and prove to you today that this is not the case. And one aspect of recognition that's definitely not solved is grounding. So consider this problem right here. There's another image. I ask Open Flamingo, what is this? Departure board at an airport. Correct, right? Okay, which way is 413? Straight, right? What does flamingo say? To the right. Wrong. What gates are straight ahead? What does flamingo say? A, B, C, D, E, F, G. Okay. Thank you for the alphabet, but definitely not the answer, right? So yes, categorical understanding of images is a well-thought and well-studied problem. It's no surprise that we're seeing better and better solutions. But as the tasks get more complicated, there is no such thing as problems being solved. So apart from grounding, apart from this grounding problem that I just showed you, another problem that's completely unsolved is 3D from a single image. So here's an image I downloaded from the internet. So not a robot, not a standard, just an image that I downloaded. And I'd like, as I'm a computer vision researcher, to understand 3D object properties of the scene from this image alone. What is there? What can I do today? I want to know how far away the bus is from the camera. I am taking this picture and I want to know how far away the bus is. I also like to know how big the bus is in meters. These are all computer vision problems that we don't have solutions for today. We do have some progress in depth estimation, but it's not actually metric depth, it's not absolute depth, it's actually relative depth. So it tells you mostly how objects are kind of, which one is closer to the other in relative scale, but not in absolute scale. And also it suffers a lot from faraway objects. So I don't think that we can claim that any computer vision or recognition is solved. Well, we can do basic things like this. And this is exactly the types of problems that I'm very interested in solving and very interested in exploring, actually. And we in the CVPR, we're proposing this solution to the problem of 3D object understanding through Omni3D that we'll be presenting this Wednesday in the poster session. But apart from this 3D layout that objects have, they also have shapes, and they have interesting shapes. Here's another image from the internet. Actually, it's an image that I took with my phone in my collection, so it's not from the internet. Do you recognize this object? Yeah, okay. I can't believe that you guys are no Spyro. Do you not play Nintendo? Okay, wow. I culturally am probably very old, but Nintendo rules. So I'm shocked that you guys don't know it, but I'll get over it. So you have, but this is great. You've never seen Spyro, so you don't know who Spyro is. But so I'm showing you this image, and yet I think that you can tell the shape of this object, right? If you were asked to pick this object up, you know exactly where to expect that there will be mass and there wouldn't be mass. So nothing would surprise you. And yet, can we predict the geometry of this unknown object today with a computer vision model? Again, a problem that seems basic. You can do it very easily, and there isn't a computer vision system to do it. Again, recognition is not solved. So don't believe whatever you hear. And so this is exactly what I want to talk about today is how can we build computer vision systems by taking a single image of an unknown object, even though you should know Spyro, but unknown object, and predict the 3D geometry of that object, no matter how complex the object is. So two aspects of this problem of 3D object understanding, pushing the limits of recognition to 3D. I will not talk about the first one. I will actually talk about this later today. And today I want to just focus on, in this session, want to focus on the problem of predicting 3D geometry from a single image of any objects. And this is work with some great people from Meta AI. So 3D reconstruction is a very well-studied problem. It is a problem that a lot of people have tried to find solutions to. And it's important to note a few properties of that research. So one is data sets. And one data set that has been driving this work forward is ShapeNet. I have many feelings about ShapeNet. And even though I'm not a big fan because it's synthetic data, simplistic, you see a lot of work on models that try to do very smart things on just renderings of objects on a white background. There is no doubt that research through the ShapeNet data set has led to great work and great findings, especially through representations. And thanks to this work, we've actually been able to maybe push 3D reconstruction forward to moving to real images, objects placed in real scenes, and reconstructing their shapes. And even recently, there's been some even more exciting work on text to 3D. So this is highlighting 2 papers from OpenAI as if they needed more advertisement. But the reason why I'm highlighting them is because they use the same representation that we do that I'll present later on. And in this work, they go from text to point cloud representations. And also a favorite paper from the recent one, 0123, which takes an image and reconstructs a novel view, so synthesizes a novel view of the object in the image from a different viewpoint. So 0123 does novel view synthesis, so some of those new views. You could extract geometry potentially from running some sort of structure for motion algorithm, but its main focus is novel view synthesis. But something that has emerged from all of this research and all of these findings in the recent years in the state of AI and where we are today is that we care about generalizable solutions. I don't want to see a solution that's trained on ShapeNet and tests on ShapeNet. Who cares about ShapeNet? We don't want to apply our models in domain. We want to go out of domain. So if we want to get solutions for 3D reconstruction, I want to be able to take these very imaginary objects that my model has never seen before. I assume that you all have seen spiral, but in this case, it would also be spiral, but definitely I've never seen these objects. And yet, I want my computer vision system, just like my human vision system, be able to reconstruct the shape of these objects. I've never seen this before. These are DALL-E generated. So how can we build computer vision systems that go from single image to 3D for all types of objects, no matter what they are? And so this is sort of the push we try to do in this project. I'm not claiming this is solved. What I'm stating here is the problem definition, okay? And so our North Stars were reconstruct any object from a single view and learn generalizable class-agnostic 3D representations. And perhaps the latter will help the former. So the work and what we were inspired by here was MAE, masked autoencoders. How many of you are familiar with MAE? A few, okay. So MAE is this model and the technique that was developed for self-supervised learning. So it promises to learn generalizable, general purpose representation by learning through images, where these representations can now be used for downstream tasks. And the way they do this, the way Kai-Ming et al. Did this set up MAE is they concocted this task, which takes an input image, it patches it, some patches randomly are masked out, and now they're training on a code-decoder network to fill in those patches. So this is a made-up task. And what we're hoping, and they found to some degree that it's true, is that by trying to solve for this made-up task, they found representations that are general purpose and could be used for downstream applications. So we were inspired by MAE, but there was one important observation that we made. And here's the observation. So here's an input image. This image of an object where you see only part of it. So this is what I would get if I had a depth sensor, if I had a depth modality for this image and listed it in 3D. I would get the 3D shape of the object that is visible from this view, but the rest of the object is missing. So what happens if I now train a network to predict, to fill in the missing parts? This is exactly the MAE setup, but now it's not made up. It's actually a very natural setup, because in 3D, you always see from a single 2D image, you always see one part of the object. The rest of the object is hidden naturally through self-occlusion. So the question is, can we learn generalizable representation by learning these models to fill in the missing thing from the scene thing? MAE said that this could lead to good representations in 2D, so this should lead to good representations in 3D. So this was exactly what our motivation for this work. And this is exactly what we did. But it turns out that to solve this problem and to actually get to good representations, there are some aspects of the model design that are crucial. And now I want to cover how we set up and define the model to do this task. So given an input image of an object, first, we feed this image through an encoder, an RGB encoder. So this is an encoder model. It's a transformer base that takes in the RGB image of that object. We follow the VAT architecture, exactly the same. The VAT architecture takes an image, it breaks it into patches, which that now get linearly projected. You add some sort of position embedding, you make it into a sequence, and now you have a transformer model on top. This is regular VAT. Now, we assume that we have some sort of depth modality from that image. We are assuming modern sensors. We don't really need to go to the extreme depths of image to 3D, since any modern sensor today actually has depth. So we assume another additional channel, which is the depth view, which is when we unproject it, leads to this point cloud of only the visible shape of the model in the image. And so now this point cloud, we feed to another encoder network, which this time is also transformer based, but it deviates a little bit from the VAT. And the reason why it deviates, because we no longer encode RGB images, but we encode XYZ points. So we deviate a little bit, and actually we deviate in the patchification aspect of the model. So the way that we actually break the image down to patches in order to do this. And actually, just a few details, the way we do this, we literally encode the XYZ positions, and then we do local attentions to get patches instead of defining what the projections are as in VAT. So small change to the VAT, just to the fact that we're handling a different modality, not an RGB. So these two are now the encodings of my input, the encodings of my object at train time from the RGBD view. If they form the memory, the keys and values, the queries are nothing else but queries of in 3D space, the 3D points in the 3D space that I wanted to code. So they're nothing else but points in 3D space, which are now fed to this decoder network. So the outputs of the encoder is the keys and values, the memory. I have my queries, and all the decoder is asked to do is predict whether the points are occupied and what their color is. And again, the decoder is transformer based. And at the end, what you have is, if you can do this task right, is that you filled in the geometry of the object holistically from the 360 view. Does that make sense? So what are some good properties of this model? So first, it only needs point supervision, which is great. You don't need meshes, you don't need CAD models, you don't need any of that. All you need is points, and points are easy to get. You can get this with this, you can get it from structure from motion, or if you have videos. Points are easy to obtain with modern sensors and modern algorithms. So that's one. So supervision is easy to acquire, the easiest you can hope for in 3D. Class agnostic, we wanted to move to a class agnostic design. That was a lesson from MAE into building generalizable representations. And also the network is very simple. It's transformer based, but it makes no price about the objects, no canonical poses, no convex whatever, no price whatsoever. Any object, any shape, at any orientation. So we trained this on real world data. We use Code3D. Code3D is a data set of videos that people took of objects. So it's 360 captures of objects of over 59 object types. So you have about 37,000 videos, which amounts to something like 400,000 images. And if you run structure for motion on these videos, you get these point clouds, which are now we're using them as supervision. These point clouds that you get from structure for motion from real videos are actually very noisy. So it's nowhere near clean ground truth, but at scale, noisy labels are good. Actually, they're the best we can hope for. If all of our solutions relied on clean annotation, we would be nowhere. So noisy labels are good, but because they're at scale, so that is completely fine. So this is where we train our model. And I want to show you some results of what the model does and what the model can do and how we can build this and extend this in the future. So the first thing I'm going to show you is results on this data set. So I told you that it has 51 object types. So what we did is that we broke the object types down into train, val, and test. So our test set has novel object types. So we have never evaluated on types of those objects. For example, in this particular case, we have our test image of a backpack. Our model has never seen a backpack before because we broke our categories into distinct categories in train, val, and tests. So it has never been a backpack before. It was the cleanest way of evaluating things so that we don't overfit to object priors. So here is the point cloud from this view that you get from the structure from motions. And you see it's very noisy. You see some points are like somewhere in the 3D space because structure from motion is going to be noisy. You can't avoid that. So these two are the input to our system. And this is the resulting reconstruction from our model. So you see that it actually cleans up the points that are noisy. And it also fills in everything that's missing in the input point cloud. Yeah. Yes, so we do segment out the foreground object and we use SAM for that.
Okay, so you remove the background.
The background is removed, yes. But as I said, testing on the data that you train in this is not what we're here for. This is the past. We need to move to general purpose solutions that can work in the wild. So we want to see how it works out of domain. So here's some results from iPhone capture. So we use our iPhone and captured objects from our house. So you see the input image, you see the point cloud that the iPhone 12 camera captures, so it's a LiDAR camera, so I can get point clouds. My model was never trained with iPhone LiDAR outputs. It was trained with structure from motion point clouds. So it has to also generalize that aspect, not just the visual domain, but also the depth domain that it sees during training. And the reconstruction is shown on the right. Another example from our house, like Mark Zuckerberg's favorite toy at the moment. iPhone capture, this is the LiDAR output and the reconstruction on the right. And I think this is some of the co-authors' plant that he has on his desk. Again, LiDAR with iPhone and the reconstruction on the right. We can also do this with an imaginary object generated from DALL-E. This is, I think we prompted the DALL-E with a marshmallow with a mustache in the shape of a cat. Okay. We use Midas depth. The images in DALL-E do not come with depth, so we use Midas depth here. Again, my model did not see Midas depth predictions. So structure for motion again needs to be generalized here as well. And you get the reconstruction. A capybara with a hat, same deal. And obviously, all methods, and this is something that you should bear in mind, have limitations. And the biggest limitation that we saw here was actually not in the space of in the novelty of the visual domain, but with errors in depth. So if your RGB view is actually the B channel is actually inaccurate, like in this case, you all know that, right? Yeah, thank God. My iPhone had kind of messed up with the ear. It thinks that the ear in the left is kind of positioned in a weird way. I don't know if you see it. And then my mom kind of awkwardly tries to communicate like that, and my ear is a little awkward. So it tries to do the best it can, but if the error is very off, then that is a limitation of the model that it can simply not overcome. But one of the most interesting results from this work is going beyond it. Something that I want you all to bear in mind, I say this every talk now because we live in weird times. No paper that you see in the CVPR solves any problems. It is. It adds a little bit of something to the solution space, but no problems are solved. So don't believe tweets and Twitter and AI influencers that say that, oh, this is solved and this is done and whatever, okay? You're all here when you're smart, so you can think critically. So please don't believe what you hear. So, but what is important to understand is what are the limits of the model and how we can expand and how we can improve it. So we spent a little bit of time trying to study the scaling laws of this approach. And essentially what we want to see is that how the model behaves as we increase diversity in the data. There's two ways you can increase your data. You can either add more examples, more examples of the same object types, or you can expand on having more object types, so add more categories of objects. And we found that the most promising for performance is to actually increase the number of categories in your training data. So have your model see more object types, so it has bigger diversity of all the objects around in the world. And that makes a lot of sense, that this is the biggest, this is what matters more for the model to work best, or this seems to matter more for better performance. And what this also means is that if some of you wanted to collect a new data set, you should be adding more categories rather than adding more examples of the same categories. And what is very exciting right now is that in a few weeks from now, there's going to be a fantastic new data set released from the Objaverse team and Matt from UW. This is Objaverse Extra Large. It's a colossal universe of 3D objects. It has 10 million 3D objects of all object types. So there's no curation of object types. The diversity in categories and the quality of texture is actually some of the most higher quality data set I've ever seen. And this could be definitely a data set that would benefit a lot of models, including this approach, including 0, 1, 2, 3. It goes up in the scale of data for 3D. And all of these people that want to train foundation models for 3D, this is like going to be the test spec for that. So I'm very excited about this data set. There's going to be a lot of great potential for 3D understanding. And I'm done. Thank you.
Thank you, question.
Great talk. I have a question about the categories. So do you think it's a matter of just having more diversity in the data, or that maybe one of those categories starts having more relevant examples here about sets? And suddenly see this going.
Yeah, I mean, this is a good question. It's hard to tell because we're dealing with 51 object categories. We tried hard to make it so that, for example, orange and apple, they're all spheres, right? So they should actually be in the same, they shouldn't be separated as being eval, like novel shape, because it's not, it's just a ball, it's the same. So we try to make a case for that, but it still suffers from selecting it ourselves. I do think that conceptually makes sense that you want to add diversity in the categories because you want to see more shapes ultimately rather than more texture. So yeah, but I think that, it's just kind of a hypothesis at this point. Scaling laws only matter if we can actually apply them, right? Just having scaling laws for having scaling laws is not interesting. So yeah. Yeah.
So most of these objects are rigid, right? And getting.
What do you mean? Yes.
They are not different.
Yes.
And getting point clouds for rigid objects is more difficult. Do you think that
through structure for motion, yes. Through lighter, no. Through structure for, so first of all, yeah.
So what I want to ask is like, do you think that these approaches will, when enough data for rigid objects would be generalized like for rigid objects like animals, or do you think that we need to also get these sort of training data also for non-rigid objects?
So I mean, I understand your question. But there's two aspects to it. One is how we're going to get direct supervision for non-rigid objects. So how am I going to get point clouds? And then the other question is, does my model generalize to non-rigid objects if it was trained only in rigid? Actually, we have a lot of examples of animals on ImageNet. We'll show them here. So the thing is that for this model in particular works from a single image. So whether your model is deformable or not does not matter because you're only capturing one single image. You go from an image to a traditional 3D. I agree with you that it's going to be hard to get point supervision in the training set if there's a person moving and you try to capture the data, but it might not be important. You might not need it. If you have enough diversity in the training data, even from static seeds, then that might generalize to animals as well. And this is what we saw with this work. Like we have elephants, we have bears, we have all sorts of things. But I agree, it's hard to get point cloud supervision for 3D, but we might not need to get there if we have enough data, training data from other objects. What about the other?
Thank you. I'm excited to introduce Katerina, but that's Becky. Okay. Okay. So Katerina is an assistant professor in computer science and in the machine learning department at Carnegie Mellon. Prior to joining the CMU, she spent 3 years as a postdoc researcher, specifically with General Malik, and then at Google Research Mountain View, working in with the VD group. And she did a lot of fantastic work in 3D vision and team composition, and I'd like to hear about her thoughts on future directions.
Great,
Please
thank
take it
you.
away.
Thank you for your invitation. I'll start. So in the introduction remarks, Mohammed talked about language and language and vision for 3D point cloud object detection. And my question is, do we really need language for compositionality? Why language and compositionality are always presented together? Okay. And we have a model, we call it BUT-DITER, bottom-up and top-down transformers, that essentially was developed along with the 2D and 3D version. It takes a language description, the plant on top of the end table, and it takes a point cloud, and there is some self-attention on the language stream and attention on the visual stream and cross-attention, and can locate the relevant concepts, right? And this was done very early, and since then, it has really taken off how we combine visual streams and language streams for open vocabulary detection. And this is still, state of the art on the benchmarks that were referred. But the question is, do we really need language? Is compositionality and language the same? And what I'm showing here is a centaur. So I know it's a centaur because I'm from Greece, and centaurs lived in ancient Greece. But many of you, even those that don't know how you call this creature, you can still understand, it looks like a human and it looks like a horse. So you don't need language to understand, to compose these two meanings and figure out, okay, it's a human and a horse. And by the way, it's not just human and horse, because I speak in language, so I say human and horse. You're talking about specific pose of the human and what he's holding and where he's facing, and you can infer all those concepts and sub-concepts without actually even knowing how to call this, all right? Okay, so where does this compositionality then come from? We're very, very inspired by Moshbar. So Moshbar is a psychologist that talked about the importance of analogical reasoning in the human brain. So he said, I'm pretty sure all researchers have told you multiple times in any, talk you show up that, oh, yes, the human brain is predictive, is trying to predict the future, okay? Now the question is how this prediction happens, okay? So what Moshbar says is that we have some explicit memory of things where we link the input to things that exist in the memory, and we find associative links between the input and the memory. And when we predict the future, we don't predict from scratch. We essentially have scripts in memory about how the world looks and how the world works. And when we predict, essentially, we modify those scripts from external memory. And so we have a recent work. So what Moshe says essentially is don't care about how things, what there are and what is their language labels. Care about what they look like. and what you have seen in your past experience that you can compose to generate the novel concepts. So this means that the label space is not a softmax over a fixed vocabulary, or it's not even, you know, some just language description, is your past experiences themselves. Okay, and I'm going to be very concrete on what I mean in a few slides from now. So this is something that I'm very excited about. We have a recent work in ICLR 2023, where we built transformer models, you know, trained end-to-end for this task of analogical reasoning. Okay, and specifically we apply them for 3D scene parsing because it's our favorite, you know, task in the heart of all of us. But of course, this architecture is not tied to 3D parsing. We are working on extending this manipulation and so on. So what does this mean? So let's see how today's neural nets work. You take the input, it's a point cloud, and you have a network, that network spits out the segments and the labels of the different parts. Okay, and this point cloud can be complete or incomplete. And you know, you need a lot of training examples, and you train the parameters of this network to map, you know, input to output. And the parameters of this network is a form of implicit memory. You memorize things from the training set in those parameters. But what we say here in this work is, along with this implicit memory on the weight parameters, have also an external explicit memory. And what is the difference between implicit memory and explicit memory? Is the explicit memory, of course, it's nothing new. It first showed up in Turing machines, okay, Alan Turing machines, where the external memory can grow without making your forward pass slower. While the implicit memory, as you grow it, then the forward pass also is slower. Okay, the more weights you have, the slower the forward pass. So what does this external memory will do? Well, it will supply this set of experience from us that we'll use and compose to label the input. So you have an input that it looks like a bed, you retrieve similar things from memory, and now your neural network doesn't map input to output, is not trying to label things, but maps input, related input to output from memory, and all this essentially triplet input from memory, output from memory is processed jointly to predict the output. Okay, and so this is just essentially transformers with memory augmentation, but there are some specific architectural details that make them different than just retrieval augmented transformers, which is also a variant of our method that we'll use as a baseline. Okay, so you'll see now in more details. Okay, so let's see. So just to show you, the memory essentially that is being retrieved operates as a prompt. Everybody knows what's a prompt. We use them from language models, and this memory can modulate the behavior of that neural network. If the memory has 3 segments, then the output will also have 3 segments. If the retrieve memory has 6 segments, then the output will also have 6 segments, and so on. So essentially, the neural network is trained to segment the input similar to a past memory. So here is how analogical memories look like. They are comprised of 2 modules, a retriever and a modulator. Here is the input that comes, so this is the input point cloud, and this fetches relevant past memories based on similarity of embedding. So you embed the input and you embed the different memories and you compare them. So it's just a KNN retriever. And then what you retrieve is used in the modulator that essentially does this reasoning of the input with retrieve memories to predict the labeling. And the color here means a lot. So red doesn't mean, you know, the backseat of a chair. It means the backseat of this specific chair. And this brown means that this bottom is not just the legs of a chair, it's just the legs of a chair that look more similar to this actual chair that I've seen before. That's why when you see a new chair, you don't just parse it as, oh, back and seat and legs. You're like, oh, this back actually looks exactly like the chair of my grandmother's house. Okay, so basically what you project, what you see is to you closest to your experiences as opposed to a dead and fixed language space. So again, I'll go into details about how to do that exactly here. Okay. Okay, so we have these modules. Each module, of course, is neural. Okay, has neural nets and is trained end to end. Now we'll see how much end to end it's trained for the task. Now, just to tell you from here, the gradients don't flow all the way to the retriever because there is a KNN, as I said, which is not differentiable. You can make it differentiable; it's very expensive. Or you can train it with reinforcement learning, and you can be very, very flexible of how to train the retriever. I want to tell that this was inspired by some recent works on memory retrieval augmented language models. the memories they use is, we're talking about 300 million memories. They have some approximate nearest neighbor. Given a question, they retrieve facts from their memory, which the language model consumes along with the input question to predict the output. So we're very much inspired by this type of work, and specifically from William Cohen's group. He has a lot of nice papers on this, but also many other people. Okay, so we want to say, okay, what about we do the same thing for computer vision? Okay, now of course there is some difference. So as I said, the colors show the correspondence between the labeled in the memory, and the labels are all memory parts. They are not just, you know, a fixed set of language tokens. So the retriever, as we said, takes a memory set, which is all your training examples or your labeled training examples. So anything you use to train your weights, you just also dump it as an external memory repository, and you embed your input, you embed the examples, and you do KNN retrieval, all right? And you just retrieve the top 5 or top 10 or top 30. And I want to tell you that this embedding network, you can just train it using a standard, let's say, non-memory augmented parse 3D point cloud segmentor, which I'm going to show. But this is the retriever, extremely simple. We're all very familiar with nearest neighbor. And the modulator now takes the input and takes the retrieved memories, which can be 1 or more, and we'll see result with 1 or 5 retrieved memories, and embeds both of them. And we use the segmentation of the training examples on how to embed them, which means we have one embedding vector per labeled part, okay? And that's why we also color them. So the red block corresponds to the red backseat, okay? And now we feed this into some cross attention. And I want to mention that along with those memory part embeddings, we also have some what we call scene agnostic embeddings, which we share across all scenes. And those that are familiar with DITER, and just to show here the connection with DITER work, the same object queries that decode objects or segments on 2D images, exactly the same queries we're using here, all right? So this is our queries. The only difference is that in analogical networks, some queries come from memory parts, and also we have a set of queries shared across all examples, much like DITER. And why we need those extra queries? Because maybe you've seen only, let's say, chairs in your experiences, and now there's a chair and you have also a piece of cloth on top of it. And guess what? This cloth doesn't match to anything you see in the memory. You're going to be able to segment it without being able to recognize it. Okay, you're like, okay, I know this is separate, but I don't know what it is because I cannot correspond it to my experiences. That's pretty much it. And now those memory part embeddings essentially as like slots that need to be filled while you carry inference in the current scene. And here you see that we filled the red slot and the green one and the brown one, and many others we didn't. You know, many other slots will just say, you know, they just don't exist here. And the beauty of having explicit examples of how the world looks is that if I see a chair, for example, that looks like the chair I retrieved but has less legs, then I'll be able to get surprised because I have explicit priors that tell me, you know, how many, let's say, parts an object has, and so on. Okay, so this analogical networks is the combination of the retriever together with the modulator. And as part of the inference, as you see, we reject some queries and we use some of them. And this is trained with standard, let's say, Hungarian matching losses. Okay, much like detection transformers. Now, here is the interesting thing. We will train this network using a set of segmented training examples, but we will never use semantics. Okay, we will never use the fact that all those chairs, this specific part is the back part. Okay, which means that you have explicit correspondence from scene to scene. I will be able, that's why you see the, you know, each instance is randomly colored. The parts are randomly colored because there's no correspondence between them. Okay. You know it's a separate part, so you can train your segmentation transformer to segment it, but there's no softmax. You know, in these 2D segmentation transformers, we always segment the part using this inner product decoding, and then we have a softmax for each part to assign it a label. There's no softmax here, okay? There's no fixed. We want to get rid of this fixed set of language labels and so on, right? We said our whole experience and parts of our experiences will be our vocabulary. Okay, that's the whole point here. So then how can we get this scene-to-scene part correspondence to emerge in analogical networks? We will do some form of self-supervision through augmentations. Augmentation is something that, something that really works in computer vision, and we'll use it also in an analogical framework in the following way. We'll take a training example and we'll augment it twice, and we'll use one augmentation as the input and the other augmentation as the memory that will drive the parsing of the input. And because here, in this case, because we ourselves deformed the 3D point cloud, we know exactly which slot should claim which points, 3D points, okay? And because we know that, we're not just going to use some Hungarian laws that says, okay, do a matching, make sure that, the decoded parts can grab the segments and so on. We will have a much stricter laws, which we call the identity laws, that will essentially enforce each of those memory part embedding queries to decode the right corresponding segmentations, okay? Because we know how to, match parts between augmentations of the same scene. Do you see? So here we say, okay, the blue slot should, capture this, and the green this, and the red the last one. And then we're going to go to cross-scene training, which is, the full architecture. By the way, for within scene training, we don't have a retriever. We don't need to retrieve. As I said, we manually supply the memory using an augmented version of the scene. And now in cross-scene training is the standard thing where we put this weaker loss. And we jointly train the model with within scene training, so it doesn't forget the correspondence, of course, and cross-scene training. And the incredible thing is that the performance on semantic annotations is the same as a model, a baseline model that has been trained with semantics, and I'm going to discuss what that baseline is. Okay, so one version of our model, well, this is retrieval augmented D3D. Maybe I should discuss first the D3D, but we will get to that. So retrieval augmented D3D is something that is very intuitive, which is the following. I have an input, and instead of worrying to map it directly to segments and row labels, I will retrieve training examples and encode them into part embeddings, and I will also attend on those part embeddings while I assign my scene agnostic queries to my input point cloud. So basically, what you saw is that we removed those part embeddings. We can attend to them, but we don't allow them to operate as queries to segment parts. Do you see? So always the non-parametric query, the scene agnostic queries will be segmenting the input. And you may say this is a tiny detail, but precisely having those part embeddings claiming segments is exactly what creates that correspondence, explicit correspondence between the current part segments and memory, okay? So this is the retrieval augmented DTR. And this is our DTR3D, which we designed. And by the way, this is our baseline, and it already beats to death any previous baseline on that part net dataset that we're using, which takes the input point cloud and has the scene agnostic queries. And we also put this scene agnostic, and the point cloud features are also updated during cross-attention iterations, and we put all the, nice, important, attributes that you need. And we think that this will do very well also in your benchmark, already the baseline. But now I want to show you quantitatively what are the benefits of having memory augmented neural networks, and specifically analogy forming, okay, with this specific architecture that, memory part queries can claim segments. So we'll use the PartNet benchmark, which has multiple training categories and has 3 different segmentation granularities, and many previous methods only, train a different model per category, or, don't use the categories that have few examples and so on. And we'll consider 2 settings. The standard setting is when you have, for each category, you have training set and the test set. And then we'll have the few shot setting that there's going to be some categories for which either have only 1 training example, or only 5, because we want to see how well the model is doing in few shot. Now, you may have seen when papers come out on arXiv or on conferences, if there are few shot, then they say few shot on the title and they only show few shot results. Okay, so basically this creates this completely delusional model that goes at test time and says, oh, I think this is few shot, I'll use the few shot architecture. Oh, I think this is many shot, I'll use the many shot architecture. While with this analogical network, you don't need to do that. This is taking care under the hood. You just retrieve, and in one case you have few examples, in the other you have many examples to retrieve, but the same pipeline runs. And the same model is used for many shot and few shot, basically. You don't need to either train or change the architecture. Yeah, so now two things can happen when you have few shot examples. You have a new category you've never seen before. For example, table or bed. And when I give you few examples, what do? Do you fine-tune your weights or not? And if you fine-tune, do you fine-tune little, or you do this robust fine-tuning that was best paper over last year, if you remember, where you average weights after fine-tuning and before fine-tuning, or you decide to, fine-tune different layers and so on. So what we'll see is with analogical networks, even without any fine-tuning, just by adding these examples in the memory set, you already do very well. Okay, so which means that this type of memory augmented architectures are also very good for continual learning. So the results on part that look like this. In the many shot, as I told you, this is PartNet from 2019. This is the model I came with the data set, is doing pretty badly, but all our models do well. All our models is DITER, the standard DITER 3D, done correctly, all right? You take DITER 2D and you put in 3D, you implement it well, and it's already a very competent model. Then you do retrieval augmented DITER, which also retrieves some training examples and attends on them. This is the green model, also does well. And then we have our analogical network with 1 or 5 memories retrieved that also do very well in many shot. And the question is what happens in few shot when you have few examples. So you see that if you have few examples, already the retrieval augmented model, which is the green, does much better. Okay, so we see that memory retrieval helps, which is not surprising because it's a way of adaptation. So the model adapts to this specific set of examples. And the other thing that we see is that the analogical network does even better. So by the way, we're evaluating on segmentation here, not semantic labeling. We said we don't train with semantics. This is just segmentation. We'll get to the semantics in a second. Now, the interesting thing is that while DITER 3D, which is the parametric alone neural network, improves dramatically with fine-tuning, you see a huge jump, even for 1 shot or 5 shot, our model improves very little with fine-tuning. It's already very good, okay? So basically, memory augmented models can, adapt naturally in few shot setups without adapting their labels. So they are very, very flexible. So these are the main things to observe here. And here are results on label propagation, which is semantic. How well can we label now the semantics of objects if my training set also has semantics in their parts? So which means that after training only for segmentation, every segmented part inherits the label of the memory part embedding that decoded it. Okay, do you see? So we label things simply by label propagation through these analogical links that our network forms. And as you see, analogical network does already very, very, very well in comparison to DITER 3D. While DITER 3D has been trained with semantics, has a softmax, has been trained to assign every part to, the right part label. So the weights of our network has never been trained with semantics, which means that we achieved what we wanted from the beginning. We want the label space to be the whole set, the whole experience set and their parts. So here are some examples of what are the retriever retrieves. Okay, is this the input? These are different retrieved examples. And here is the results of the modulation. This is the input, this is a memory that was retrieved, and this is the analogous labeling that is inferred. Do you see? So basically different, the chairs are different, the labs are different, but the labels, our network can transfer the label. Also, you can see that there are these black things. So the network realizes that this is a new part. It cannot use parts from the retrieved memory, so it decodes it with a parametric query. That's why we see it in black. So it knows it's a different new segment, but it cannot put in correspondence. It cannot recognize it by mapping to the memory. Okay. Yeah. So this is the output of our network. It has this and this as new parts. And so this is the same results for novel classes that we didn't train on. We only have very, very few example. And you see that we have a memory and we transfer the labels of the memory very well. And so here I just show a single memory. And this is the most interesting, I think, picture is these are memories that our retriever did not retrieve. This is what we manually supply to the model. So we said, okay, your input is a TV, but here is a clock. How would you segment a TV by looking at this clock? And the model said, you know what? I don't think I can find this part. Okay, it doesn't exist. I cannot find this part either in correspondence to the clock, but you know what? The green and red, I would assign them this way. So you see the spatial abstractions essentially emerge between different object categories. The same way you can imagine segmenting a table. You have a table segmentation, you'll map it to an elephant segmentation because you understand that the legs of an elephant are similar to the legs of the, let's say, chair. So the takeaways here is that we have fast adaptation with analogy foreign transformers. We have fast adaptation to new examples, my memory expansion without any weight updates. It unifies many shot and few shot inference, and memories can prod the relevant subtasks without having a task embedding, like a 1D embedding to tell you, okay, what is the task? You just give a memory prompt. I mean, this is a very different paradigm than what has been used with parametric law networks. We are exploring how this can be adapted to 2D segmentation, as well as to manipulation, where we really want to learn for single demonstration to guide exploration in different setups. Okay, so thank you very much for your attention. Nikos and Martin are the main students that worked on this, and Shaban and Andy are other collaborators. And you can go and there is code for this. Even if you just want to use the baseline, it's still there. And you know, I hope you find this useful. So thank you very much.
Thank you. First, thank you. This is the great work. I'm really impressed by the results. Like, I want you, can you comment more on the retrieval component? It seems that it's quite critical to design it properly to achieve good performance. What are maybe the designs that worked well in your design? What maybe the designs that maybe tried but didn't work?
Yeah, very good question. So how is the retriever trained? So what we did is we trained our baseline DITR3D. We took the backbone and we dumped it into a retriever, and that was it. Now, the truth is that there are much better things you can do. First of all, the first wrong thing here is that we retrieve based on a holistic object embedding. Ideally, you should be retrieving based on localized part embeddings, and then attending to them and doing the analogous, you know, modulation. And we have discussed with William Cohen that he's very much into memory of many language models. There are incredible, you know, progress there of how do you train these retrievers, or freezing the earlier layers and adapting only the latest layers and trying to combine, you know, differentiable with non-differentiable methods. And I think there is a tremendous, you know, possibilities on training this end to end. Yes.
Thanks for the great talk. I have a question about the semantics. So you mentioned earlier that you want to get rid of semantics, pixel patterns. But it seems like once you use a specific course, like how you try to stay in the specific course, sort of imposes some semantics on it. I know this is the speed, it's the one. So do you think we can get away from that? Or do you think that's like efficient points in fine power?
Very good. Yeah. So your colleague is asking. The question is, okay, you said you didn't use the label. This is the backseat, but you used the segment, and the annotator to segment that he was thinking about the backseat in the first place. Yes, this is correct. Now, how would you use this framework in a different setup? For example, for manipulation, there's not going to be any semantics. What you're going to be retrieving is where the gripper touched. Okay, this is your important entity that you need to slot that needs to be filled in the new, let's say, scene, and so on. So, yeah. So I say, oh, I picked up here this object in analogous way. So let me take this action or gripper pose and apply the analogous pose here. Or, you know, in that previous experience, the bottle fell in that way. What would be the analogous way of it would fall here and so on? Yeah, so it's not going to be labels, etc. Yes?
You asked me something you had the block and then it was massive.
Yeah.
And understood the end of the block is same with everything.
Yes.
Like, very fascinating. on a parallel direction, there is like some work on finding semantic correspondences in images. Like where you have a dog and you have elephant, not an elephant, but a cat. And you know the nose of the dog is, you can correspond that to the nose of the cat, which is very interesting. It's not the same as this, but I was just wondering that CAD is such a method of using an explicit memory we apply to point to point. So what you're doing now is like part to part, like you have a leg in one and a leg in another. But can this, like, does it make sense to do it for like not part to part, but like point to point pixel?
Yes, absolutely. So the question is, what about pixel to pixel matching? This architecture, in fact, we had an architecture and we went to CVPR 2022 and we saw GM flow poster. And as soon as we started saying, okay, remove it, we're going to change the architecture, is directly inspired by those image to image correspondence methods that do self-attention cross, self-cross and so on. And they find the menus and then they match them. So the idea is that, you know, pixel to pixel is good, but people care about parts and they care about gripper actions and they care about how things move and fall. And how can we, in fact, it's the other way around. How can we bring whatever we know for correspondence, right? That has been around for like 30 years. In fact, what we realized with this work is Takeo was correct. Correspondence are the three most important problems in computer vision. And take whatever we know for correspondences and put it into labeling. You don't need to think differently about labeling pixels or labeling segments or now image labels. And each one of them is a separate problem. It's all a matter of correspondence, compositional correspondence in terms of your memories powered by neural network embeddings. Yes. Yes.
It's really cool to see like this transformation from like one object to another. So I was curious in your next talk also about the limitations where like topology changes. For jazz, for instance, there are many different like channels or shapes you can imagine. And so where when the topology changes, where does this break?
Very good. So basically you have a drawer with 4 drawers and now there's a drawer with 5 drawers, and you need to understand that you need to use one multiple times, correct? Yeah, excellent question. So now how can this be taken care of? Either you need to do localized retrieval, so you should not look at the whole drawer and retrieve, which you should do, but you should also retrieve locally and retrieve multiple things and attend jointly to them and infer what you want to infer. That is my best thought here. Yes, but already you can compose topologies from retrieve examples in this way. Very good question. Yes, we are trying to figure it out ourselves here.
Maybe if you have more questions, we have also Q&A and panel discussion at 5 p.m. Please feel free to stop by and ask more questions. Let's thank the speaker again. Now we're going to cover
I don't see the screen. It's not detected. Unblocked. Okay. Okay, sorry about the delay. So again, I will be presenting the 3DCoMPaT dataset and the associated challenge that we had prepared for this first edition of the C3DV workshop. So this dataset is a joint endeavor, which has been in the making at KAUST, King Abdullah University of Science and Technology. The main idea behind the dataset is first to collect a large collection of fine-grained geometries, which are annotated at part level. And with each part, we also collect compatible material information, and sample randomly from them to generate variations, stylized variations of models. So the main advantage of our dataset does not lie in the number of shapes or in the number of categories, but rather in the fact that we have these fine-grained segmented models alongside human verified textures, and also a very large collection of stylized models, which are basically visual augmentations of our small number of 10,000 geometries. So we have 42 shape categories, 275 unique parts, 293 materials, and 10 million stylized 3D models. And for each stylized models, we have 4 equally spaced views and 4 random views. And we have a total of 16 million rendered images. Okay, so alongside each view, we have a render, a part mask, a material mask, and a depth map. And in the fine set, we have 275 unique parts with 521 average part per model. And in the core set, we have a way lower number of average parts per model. Oh my God. Yeah, okay. The screen is not shared on Zoom, really? Okay. Okay, look, I will just continue from there, because I think we need to move. But I don't see. Okay.
Where is this display? Can you make it not mirror? Is it mirroring?
No, it's not mirroring.
Make it mirroring. It might be. It's mirroring.
It is mirroring.
And then I think we'll start.
that's great. Okay. Yeah, apologies about this. So I will go through it quickly. So we have for each render part masks, material mask, and depth maps. So in the fine set, we have 521 average parts for the model, and in the core set, we have only 261. So it makes it closer to other datasets like ShapeNet part. So for example, if you have applications like, I guess, zero-shot segmentation or any kind of segmentation task that does not require and actually prefers to have a small number of parts per model, then the core set would be preferable. And if you have an application that requires fine-grained labeling and segmentation of the 3D shapes, then the fine set would be your choice. So the average part count per class is represented in this graph. So basically what we do is that we heavily restrict the number of parts in the core set. And this is the part occurrences. So if you are training a model on the core set, you're going to concentrate on the way lower number of parts, which is going to be a lot more manageable for you if you want to run experiments using our dataset. So this is a visual example of what it looks like when we go from fine to core set into segmentation level. So this is for a chair, and this is another example for cars. So as you can see, we have highly fine-grained segmentation in this dataset, which is the main advantage. But it can also be a disadvantage because it's quite hard actually to learn all of these parts in the set of shapes. So here, like in the core set, you get segmentations, but are a lot more manageable for you. So this is a pipeline that we have for 3D collation and annotation. So we start from the collection of the dataset through our partner. And when we do 3D shape editing, we perform annotation and semantic grouping of meshes at the part level. Then we sample stylized models. And we render 2D stylized views and depth maps and segmentation masks associated with each rendered view. So basically, from a part annotated 3D model, we first start by sampling a combination of materials, which are going to be associated. So for each part, we're going to randomly sample a material from a list of compatible materials which are associated to this part, and then apply it to obtain a texture model. So part of the ecosystem that we propose for this dataset is an API that is, we think at least, quite easy to use. So if you want to train, for example, from 2D data, you don't even have to download the whole set, which is very heavy in terms of storage. So you can just directly train from our S3 AWS bucket. So it's going to be streamed into your PyTorch pipeline in just a few lines of code. So you have nothing to do basically. And you can already train on the full set of stylized models. So you can sample stylized point clouds in stream easily in just a few lines of code. So for example, you can start from the stylized compressed models and then sample from each mesh in your stylized set to obtain a set of stylized point clouds, which are associated to your compressed models. Also part of the ecosystem is documentation that we have taken some care to redact and write. So you can see how to use and to sample the RGB point clouds from our models, how to project from 2D to 3D and reverse back, how the annotations are formatted, etc. So we provide a 3D browser for the shapes in which you can download each shape individually, access them, download them as well, explore them in the 3D view. So this is quite easy to use if you, for example, only need to have access to a few shapes in your application. And these are some of the possible tasks that are enabled by this dataset. So here, for example, there's 3D classification, segmentation, reconstruction, novel view synthesis, etc. Okay. So the task that we propose for this first edition of the C3DV workshop is the grounded compositional recognition. So basically what you want to do is to have models that are able to recognize the shape, but also ground each part of the shape and identify each part of the shape alongside this material. So it's a very complete task that requires basically the whole understanding of how the model is composed and how it is made of, what the materials that composes the model. So shape accuracy is just the shape accuracy of the model that you're going to train to recognize the actual shape category, but you're going to have value. So the value is basically the number of part material pairs that are correctly identified. So here, for example, this knob is made of metal, and you're going to get 1 out of 3 value point if you only identify this part out of all of the pairs. Value all is the accuracy of identifying the cabinet, but also all of the part material pairs in the whole shape. And value grounded is the accuracy of grounding also these part material pairs. Value all grounded is the accuracy of grounding all the part material pairs in the 3D shape. So these are some of the baseline results for the GCR task that you've obtained for the fine set and core set. So these are simple baselines that try to leverage 2D and 3D jointly. And these are the results of Catalia, who is here today. So she has great results, and she actually won the challenge this year. So congratulations, and I will now let her present. Hopefully she has less mishaps than me in setting up her presentation. Okay, thank you very much.
Okay,
And
start video. This one,
yeah, this looks great. Okay.
okay,
Okay.
and then I just play. Yeah,
No, it should be fine. Just switch back to the presentation. Yeah, I think.
okay. I'm trying to see if there's a way I could make. Let's suppose I do swap displays. Does that help? No, that doesn't help. That makes it worse for the people here. Huh? Okay, now I've got. Huh? Yeah.
Another way is to mirror display so that the both.
Okay,
of them will-
or maybe let's try this. Okay. No. Okay, let's see.
I think one fix could be the mirror display, so the both displays are the same. If you want, I can help you.
Okay.
Yes. Yes.
Maybe disable mirroring in the displays.
Stop mirroring.
Yes. So on screen, but the presenter view, one of those.
Yes. What? Where's this? It's the swap option. Yes. It's we can just continue.
So but now we need to swap.
Okay, there's a way to swap it.
No, so I want to now. I mean the. So we need to see that display and change the swap thing.
It's not working. I think we're, okay, it's not. Okay.
No. So we need to see that Zoom. Sorry, swap displays. Yeah, to swap this one. Yeah, that one. Right.
I don't see, okay. Yeah, final.
Anyway, I'm like done with Zoom. I want never to present on Zoom again. Okay, where were we? We were talking about. Okay, I think I went through this already. That the point is we need to be XYZT, not just XY or XYZ or XYT. Okay, so So this is an area where we have at Berkeley have been working for like 3 or 4 years, starting with Anju Kanazawa's postdoc with me. And we developed these techniques for trying to figure out how people, to lift people. So as I said, people are easy and hard in the following sense. They're hard because they are non-rigid, they're articulated, they wear clothes which make for a variety of appearance, and then they are occluded by different objects. What makes them easy is that we have tons and tons of data on people. And in particular, we have lots of data where key points on people have been marked, 2D key points, left wrist, right wrist, shoulders, etc., etc. So based on that, we can devise techniques for lifting a person to a 3D mesh. In this case, we use a simple representation. And what we do is we can train it by trying to minimize reprojection error. And this work has gone through years of development, but I'll show you what we have today. So this is a paper which is available on arXiv, and you can download the code and run it yourself. And the setup is that you have an image, you have some encoder, and it's trying to predict the pose, the shape, and the camera. And this was our approach, to have some network which spits out all these parameters. And then there's a discriminator which tries to separate it from, which uses the very small amount of 3D data that's available. And then the 2023 version of it, I mean, it essentially, okay, as always, we replace coordinates by transformers and get an improvement. That's one big thing. Second is the idea of MAE pre-training. And then the third is the idea of lots and lots of data. Okay, and basically with these ingredients, we are able to get a much better performing system. So this is the current trend towards what I call foundation models, though I hate that term. So let's see some results. So this example is meant to show you how much we can deal with all these variable poses, and you can reconstruct them. We can deal with multiple people. So here what's happening is that each person is being detected, lifted to 3D and tracked in 3D space. And here's another example. Okay, I like this thing. So the left is the input and the right is output. I think the point of this is to show that this is a problem I've had students work on for the last 25 years, and 7 different PhDs, and it's done. I think we don't need to work on it anymore. We can solve this. The problem of 3D reconstruction of people from images of video is solved. And this is an example. So that was from Michel Kwan, 1998. And here you will see a more, this is, I think this is the couple which won the championship in 2022. Okay, and so here you can see that all the pairs are also being handled correctly. And more examples. Okay, and the point that I want to make is, this is on the code is on GitHub. On Hugging Face, there's a demo. You can upload a video and you can get this 3D reconstruction of every person in the scene. Okay, so this is there. You should just use it. Okay. So I want to explain a few of the ideas behind it. So essentially, we are lifting the people to 3D, and then there's also tracking, and the tracking also should be done in 3D. And here's some examples. So like if you have these people that you're tracking, we now have the ability to lift a person from 2D images to 3D pose, 3D location, and appearance. And this gives us advantages for tracking. So suppose I want to track this person. As this person is running, what's happening is that in 2D, the person's appearance changes a lot. He's big, he's small, etc. But in 3D, there isn't that kind of change because it's the same person. So the bounding box changes a lot. So classic tracking techniques will suffer. But if you are doing things in 3D, it doesn't change so much, right? Also, the appearance doesn't change. The appearance in pixel land changes, but if you think of it as a 3D texture map on the body of the person, the guy is wearing a white t-shirt, so then that will be white. Okay, some other part of his body has black shorts, well, it's going to have that color. Those are all texture maps on the mesh of the person, and those are constant. If you look at it as a 2D pixel map, it's changing all the time. So the claim is that when you do things in 3D, they are going to be much more stable. So I really do believe that at this point in time in 2023, we have seen great progress in like 2D object detection and 2D image segmentation. What's the main problem we should be tackling? It is 3D. And 3D, or I would call it 4D, because we should consider both that. Because with those problems, when we solve those problems, we get the invariances that you get from 3D. The object appearance doesn't change in 3D. It changes only because of the 2D projection, because of the varying camera. So these are just more examples of that. So therefore, what we did was we tried to do the tracking in 3D as well. So this is just to show that we have the 3D views. So therefore, here's what they look like. And I'm going to go fast. That we can do tracking in 3D because we can do prediction in 3D. Prediction is also easier in 3D. Because if you consider somebody is moving, and they're in a short run, in a short period of time, they're always moving in a straight line, right? Because everything can be approximated by that. But in 3D, they have a constant shape and their position can be predicted. When you consider them in 2D, then it goes through the camera. And now they could be becoming bigger or smaller or this or that, which are artifacts of the imaging process, not fundamentally how the people are in 3D. So so the tracking process becomes better. So we have this paper called FALP, which was published previously, which just showed that all these tracking tasks for the case of people, we can do them much better. We have fewer errors, better at re-identification and so on if you do the whole task in 3D. So that's the model. Okay. Location prediction is very straightforward, right? In 3D, you just draw a line through the previous locations and then predict. How do you predict appearance? Very simple. Appearance is constant. Because if you think of appearance in 2D, it's not constant because the person is presenting different views. But when you think of the person in 3D, they're the same, right? The texture map on the body. It changes a little bit because suppose you're wearing a skirt and then the skirt swings in the wind, but that's a very small effect compared to the changes which arise due to camera and the person changing their body. So appearance prediction is essentially, notice these two views. There's okay, so appearance is constant. The 3D pose we can predict because we can build a model of 3D pose. So we can essentially use the kinds of techniques for prediction which have been used in language, like predicting the next word. We can use those kinds of techniques for predicting pose. right? If you have a sequence, you can delete some poses and then predict them from the rest. And as a result, just like we can build language models, which are behind GPT-2, 3, etc., the same thing can be done in pose space. So, yeah, and then we can model the cameras. I mean, there is some work which is going to be shown at this conference, which shows how we can deal with moving cameras and so on. Okay, so camera motion can be dealt with. Okay. So as a result, we can get these kinds of reconstructions, and just showing you more results. This actually helps, and there's a paper we have at this conference that having this 3D tracking and pose helps us with action recognition. So the action recognition problem right now is dealt with by taking the video as three-dimensional data, but it's X by T, and then we have run the spatiotemporal convolutions or with transformers, but the tokens are that you just divide up the image into patches and in time. Now, what's actually happening is that the person is moving across time. So what you really want is an action tube, a person tracked over time, and now you want to compute features across that tube. So, so that's the I call this the Eulerian versus Lagrangian viewpoint. So those of you who may have studied fluid mechanics, in fluid mechanics, there is a distinction made between these two perspectives. So Eulerian view is that you just stand at one point and you just keep making observations. The Lagrangian viewpoint is as if you are sitting on a particle, and as the particle is moving, you go along with the flow. Like either you stand on the bank of a river and observe the river, or you sit on a boat moving with the river. Right? So the boat moving with the river is the Lagrangian viewpoint, and that's what we are doing here. Okay, and this gives rise to, and this fits in with this whole 3D perspective. So we extract these tubes, and then we have this action recognition with a Lagrangian view. And okay, and then it turns out that with this, the resulting representations work better for action recognition as well. And here are some numbers. So there's this data set called AVA, and action recognition where we only make use of pose. Okay, where previously the state of the art was 14.1, and then we jumped it to 23. But more interestingly, you should use pose and appearance. And okay, this is a classic problem. And MWIT was the state of the art. And this is work out of Facebook with Christoph Eichenhofer and co. And then with this combination, this idea of using this action tube, the performance goes up. And our latest on this is at 45 MAP, which is, and this problem was worked on like 5 years ago when it was proposed, it was 15 MAP. So from 15 MAP to 45 MAP. And this is a very big advance for video recognition. And I think the key here is we must think of people as being in 3D. And here are some results on various tasks which are being there, recognition tasks and so on and so forth. Yeah, okay. What are the next steps? We can do learning to act from 4D reconstruction. So essentially, the field of robotics is ripe for a revolution. I always say that robotics is like 20 years behind computer vision, and it's hard. I mean, there are reasons for it. It's a hard problem, but the kinds of techniques which have helped in computer vision, which is the use of big data and benchmarks and so forth, I think robotics could benefit from that same mode of thinking. But I think what do we have to offer as vision people? One is essentially this 4D perspective makes a lot of sense there. It's not, the action labels are not so important, object labels are not so important. You really do care about that 4D perspective. Second, a lot of learning of how to act in the world is based on imitation. We observe other people and then we copy them. We observe our parents and we copy them. So if we can lift people to 3D and objects to 3D, then the robot can just copy that. And there's been work of that type, which we've been doing in my group. And there's an earlier example, which was in movement in free space, but I'd like to show you some on action. How much time do I have? Do I have 5 minutes? Or? Because, okay, somehow, huh? Yeah. So let me try to end. Okay, what do I don't want to mess. Yeah, I'm trying to end this. Okay, so I'll try to show you some results on hand-object interactions in the wild. And what you saw so far was about how we can lift people to 3D. So let's now assume that we can lift people's hands to 3D. And then there is an object, right? So there's a person manipulating, and then there's an object. So that object is also lifted into 3D. So that's where compositionality comes in. The hand is lifted to 3D, the object is lifted to 3D. And so suppose we have techniques for this. And I'll show you how we can have techniques for this. Then we are well set up for imitation learning. So all these robotic tasks that we want to do, we can learn from observing YouTube videos. And how do we do this? So there's this paper was presented. This is from ICCV 2021, so you can look it up. But the basic idea is there's an object pose estimation and hand pose estimation, but you can't do it completely independently. You have to do it together, because obviously the hand cannot interpenetrate into the object. The hand and the object should be touching, but not interpenetrating. So that's the joint optimization part. And that's all those details I'm going to skip. But this shows some of the reconstructions that we can get. So here's this lady who's brushing her hair. And from this single image, we have got a reconstruction of her hand and the reconstruction of the brush. And in the next image, you have somebody holding a spoon and then a knife and so on. So this technique is still rickety. It doesn't work off the shelf. I mean, what I showed you for human reconstruction, it just works. You can just download it and run it. This kind of technique where it's hands and objects, because the hands you don't have that many pixels on, and there's hand-object contact makes it hard. This you should regard as work in progress. Over a couple of years, I think we'll solve it, but it's not solved yet. But imagine the day when it is solved. When any video that you have, you can convert to 3D hands manipulating 3D objects. Okay, so just to show you what we can do today. So this is the hand and then different viewpoints of the hand and the banana and so on. More examples, right? So just think of what we do with robot actions today. We do simple pick and place, but think of what humans do with their hands. It's many, many more things. And those are what I'm trying to show you here. So now I'll show you a very much recent result, which is learning to imitate object interactions from internet videos. So we tried to use this for training robots. So there is some internet video, and then we can get these hand object trajectories in 3D. But actually it's 4D, right? Because it's in time. And then the machinery was what I showed you before, which I won't go into too much detail. But look at this. Okay. So we are trying to show you how the object interaction works over time. Okay, so this technology is not yet robust enough, but just imagine a future where any YouTube video of people, could be a how-to video, it could be whatever. We take that video and we get a 3D hand manipulating a 3D object. I think it's doable, but it's not there yet. Okay, we got the flavor of what this is. And in fact, we have tons and tons of examples. Okay. And note, we learn a lot of things like humans use two hands, whereas a lot of robotics work is with one hand. But we do bimanual stuff. We hold with one object with one hand. Like if I want to unscrew a bottle, I'm going to do that, right? And now the goal is to use that for training a robot. And basically, it's going to be imitation learning, right? So there's a hand object trajectory, but there's a challenge, which is that hands and robot hands don't have exactly the same morphology. It's somewhat similar, but not the same. But what you can do is to say, let's look at the trajectory of the object and follow the object. So object-centric perspective. So what you'll see in this demo is there's a video of a human doing something. And then what we'll try to do is that the robot will try to pick up the object, so it's not starting from the same position, and get it in the same final pose. And okay, you have to train this with reinforcement learning. It's trying to, it gets now a dense reward because at every frame it's trying to get the same pose. And it starts with trying to bring the object to the initial pose, and then it tries to imitate the rest of the trajectory. And let's see if we can see some examples. So that's what happens to the object, and then we'll see the robot do the same thing. Let me see if there are more examples. Again, the final pose should be the same as the human pose. So these are, as I say, I would say these are initial signs, but I think that this could be the future of robotics. And I'll end here. Thank you. And yeah, we have done one demo with actually with a real robot. Yeah, question.
Really good talk, thank you. So you said the mesh recovery is solved, however, I still saw some problems. For example, the face. The mesh is still not recognizable. How about the face? And also, I didn't see any clothing of these people. Do you think the face identity or accurate face and clothing or even hair is important for?
Yeah. No, I should have been more careful. I said mesh recovery for the body is solved. I think the face is a special part of the body, and you need to have higher resolution and do special things for models of the face. And I'm sure my colleague Matthias will undoubtedly have things to say about faces. And then hands again are different. So I'm basically excluding face and hand. I'm talking about the rest of the body. I think both face and hand need special models and special techniques. And clothing, I'm not worried about. I'm just dealing with the rest of the body. Because clothing is, yeah, I mean, that's a whole different problem.
But for your beauty slide, do you want to plan to anything about more accurate face or clothing?
No, more accurate face, I leave to people like him. Okay, I'm not interested in that problem. More accurate clothing, also I'm not interested. I want to solve the robotics problem, and robots don't wear clothes.
Thank you.
Sure.
Thanks for the nice talk. One question is about the 4D representation that we used to and we are using computer. What do you think about including language or details from language, except from language and instructions? The language about the 4DCs, the language about the human, if it was clothing, if it's included or not, or if it has a specific action, do you think that this information?
No, I think language can be helpful, but what I strongly believe is that language is only part of the answer. So currently we live in the era where ChatGPT and GPT-4 and so forth. So people think that it's all about the language, which I disagree. I think that for vision and robotics, we must focus on the 4D nature of the problem. And we need to have representations which capture that. Now, these representations connect with language. And language can provide a very good framework for compositionality and for generation. So I'm saying that language should be combined with this, but we need to have the low-level technology when we start from the pixels to get to basic 3D, which, for example, gorillas can do, and they don't have language, right? So I believe that a lot of it is possible without language. Humans have language, and language gives us compositionality, and it's very important. So I'm not arguing against language. I'm saying the two need to be combined. I object to the approach where you just say, oh, language will take care of everything. I think that language is a layer on top of the fundamental 4D representations.
We believe more on learning from the pixels than taking the high level abstraction and porting it into the models that are prior.
Yeah, because see, if you look at a description of a work like, say, standing, right? From standing, I mean, I'm standing now, but this is also standing. Language abstracts away the details of 3D space and time. And that abstraction is good for certain purposes, but it gets rid of some very essential detail. When we watch a movie because it is different from reading the novel. Because in the movie, there is this visual detail which we also enjoy. And it is not captured in the movie. Otherwise, you would say, just read the book, never watch a movie, right? Yeah. 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 No, that's certainly an area of research where you have multiple cameras and you want to combine that. I have not worked on that, and I'll give you my logic. I really want something which will scale up to very large amounts of data. If you look at YouTube has 156 million hours of video. My goal is that use YouTube to solve robotics. Okay. But YouTube, you'll generally get data from a single camera. So that is what most of the data is. To get multiple cameras, I have to bring people into the lab and collect the data, and various people have done that, but I think that data will always be kind of limited. It'll be higher quality, but limited. I want to develop the techniques which will work across the board. Last question. Yeah. Good question. So I think it helps that there is a parametric shape model, right? So the simple is one of those, right? So it gives you this mesh, and it's now like a few hundred, triangles. It's an approximation, but it's a pretty good approximation. So now that means that the estimation problem is reduced to relatively a small set of numbers, right? Okay, that's one. And then there's tons of data. And the data here is the annotations here are the key points of people, right? So so we essentially, it's become a supervised problem, and it's a problem with lots of data. Okay, and that's the kind of thing we know how to solve well. Okay, now if I want to recognize, now what we've done for humans, I don't think we can do for 100,000 categories. We won't have the time and energy to do that for cats and dogs and mushrooms and whatever, right? Chairs. So we will need more generic techniques, but I think the good news is that many of those objects are rigid. So rigidity reduces the complexity of the problem. And yeah, I think humans are very complicated and difficult and all that, but we have the advantage that we have tons of data. So that combo with very good representations, which is what we have now, has enabled us to solve the problem. Okay, thank you.
All right, you can continue, and then I can use this computer to back to your voice.
Oh, okay, perfect. So just go ahead. Just continue and then we record with the other mic.
Perfect. Okay, is it good?
Okay.
All right, then you can go ahead.
All right, so yeah, getting back to it. So 2D panoptic segmentation models on single views work quite well right now. Like we've seen great progress, and they can work quite well even in the wild images. So you just take an image and take a pre-trained model. It works quite well. So here's an image from my desk back at TUM. And if you run it through Masterformer, you get quite nice segmentations here, right? Like, so you see like just pre-trained model gives really crisp boundaries. Most of the instances are separated quite well. The classes, it gets quite a lot of them right. So it's quite at a good stage now, right? But when you try to make them work across multiple views, you see a lot of problems. So as an example here, you see in the middle, the semantic segmentation, it ends up predicting the couch to be sometimes a bed, sometimes a sofa. So it ends up like not being consistent in the end. You also see that the segmentations in the middle that I show as red, it sometimes just fails to predict any class. So there are these issues. And if you see on the right, the instance segmentations, they keep changing the IDs across all the views because it's a single view model, right? Like it's going to assign the instance IDs again and again and again. So there's no consistency across the instances. And when we want to work across scenes, we actually want this to, be consistent. The same object should be assigned the same label, right? So how do we solve this? So our method takes RGB images from a scene and also the predicted 2D machine-generated label, so from an off-the-shelf model, and then lifts it to a 3D volumetric scene representation, where you can just take a camera, move along the scene, and then volumetrically render it to clean and consistent semantic and instance segmentation. So you get a complete panoptic representation of the scene. It's 3D because you can also get the depth, you can get the semantics. So all that's going into this pipeline is just RGB images, right? Like everything else is pre-processing. The cameras we got from Colmap. The semantics that we use for optimizing the nerf are coming from they're coming from Masterformer. So it's just RGB images that you start with, and you get this whole panoptic understanding of the whole scene. So how does it work? As Matthias said, like we build up on nerfs, and as you know, nerfs take in a position and a view direction, and they have this density and color heads, right? We additionally add two heads, semantics and instances, and because we are also predicting these as fields. So whenever you want to render one of these fields, the color, the semantics, or instance, you just take opposed direction, you render the rays, and you get an image out, right? So a little bit more about specifics in terms of the nerf architecture itself. We build up on TensorF, which is like a fast nerf. So instant NGP TensorF came up around the same time. This was like a PyTorch only version, so I went with this. But the main goal here was to use this because TensorF just speeds up training time and inference time, right? For the semantics and instances, we used just a bunch of small MLPs. And this decision why we didn't use, I don't know, a grid representation was just to save memory and also have smoothness, right? Like MLPs implicitly have some smoothness in them. So yeah, TensorF using this as an architecture speeds our method up. And how do you optimize it? Color optimization in nerfs is very, like a lot of people know it by now. Like you just render rays and then take an L2 loss with the observed images that you have in the scene. We do the same thing with semantics, right? Like you render semantics, the classes across array. And the predictions that are coming from Masterformer I use as ground truth. But one thing is that instead of using one hot target probabilities for supervision, we actually use a distribution over classes. So what we do is we take the images. For the same image, we perform test time augmentations, and we run it through Masterformer again and again, right? Like they're all different inputs because we're test time augmenting them. And we get a probability distribution as the target. And we also get confidences out. And this actually helps quite a bit in terms of the IU and PQ scores, which are used to measure semantic and panoptic performance. So this is one thing we do. I talked about how this semantic segmentations coming from Masterformer are quite inconsistent, right? Like, so if you see in this example, you have, okay, the right image doesn't seem to move. Yeah, but like as the camera moves, you see that it's sometimes predicted to be a chair, which is correct, but sometimes as a toilet, which is not correct. And we want to handle these kind of non-robust behavior, right? And one implementation trick here is that a lot of times, well, like people, when they use semantic fields, especially in the earlier papers, they tend to predict logits as the output. But what we propose is that instead of logits, you should predict probabilities because they're bounded. And this is really important in the context of these neural, these nerve-like models, that whatever you predict out of the MLPs, it should be bounded, right? Otherwise, like, let's say if you have two separate points and they have viewpoints and they have different labels. So in the example that I showed was a toilet and a chair from different viewpoints. The volumetric rendering could make it so if you use logits, like the optimized nerve could still make it look like a toilet from one view, but like a chair from another view. And if you end up using probabilities, it makes it bounded and this behavior cannot happen. However, even with this, the nerve can cheat because this gradients from semantics can still go to geometry. And then what happens is the nerve starts creating clouds to satisfy that label, right? Like, so when it goes to the area where the label was wrong, it starts making clouds and give it that label. So to fix this, we say that, like, okay, semantics should not try to fix the density because semantic labels are noisy for us and we should not trust them for the geometry aspect. And this again gives us some benefits. However, if you do both these things, you can still end up with a compromise for the label, right? Like, because it's a normalized cross entropy loss, what the optima would just be a compromise between both of the labels. And for this, we propose this segmentation consistency regularizer, which is based on the observation that when you get masked to former segments, and if you take the class away, they're correct, right? Like on its own, it says, oh, it's in this view, it's a single segment, whatever the class may be. In another view, it's also a single segment, whatever the class it may be. Okay, the class is wrong, but the segment itself is correct. So our regularizer says that all the rays that belong to the same segment should have the same class, whatever that class may be. And once you apply that kind of regularizer, you see that our problem of these compromised labels that are somewhere in the middle gets solved. So just as a quick recap for what we're doing for noisy predictions here, we get clean and consistent segmentations because we're handling all these segment consistency things. We're blocking the gradients. We're using a bounded field. So this all results in a more stable behavior. One thing I didn't talk about until now was how do you handle instances which keep changing across views, right? So you cannot just apply the normalized cross entropy loss on the instances because at each frame there will be a completely prediction and the IDs would keep changing. You cannot just use these IDs for supervision. So how we solve this is we render our field and based on the probabilities of what the current state of the instance MLP is, we create a linear assignment between your currently predicted labels, so the network's currently predicted labels, and the ground truth labels. And then we create this cost matrix where the entries in the cost matrix are dependent on the current probability states. And it basically what it does, it creates a mapping from the masked to former labels, which are 2D to the 3D labels that you're currently predicting. Once we have this label, they're all in the same space. So they're all in the 3D label space, and you can actually apply this loss. So once this is all done, yeah, this is our method, and you can just make it run in the while scene. So this is my dorm room, and you can just take pictures of the room and optimize your nerve, and you have the labels, so semantic segmentation, instance segmentation, a whole panoptic view of the scene. And there's another room from Tom. So a lot of chairs, and you see all these instances are separated quite nicely, and you have a free view control on the camera itself, right? So yeah, we also compare with other methods. So semantic nerve was one of the leading works in this field where they were only predicting semantics. We add instances on top, right? And we are also more robust to the quality of results here. I don't know why they're not in sync here, but okay, let's move on. So there's TM nerve, which is also quite a related work, but you see here that they're also not that robust. PNF is perhaps the most closest work, but again, they suffer from like not so robust behavior because they're using 3D bounding blocks coming from another network. pre-trained network. And like if you have these 3D models which are not so robust to start with, you end up with a method that's not so robust. So that's one problem. So there's another comparison on scanned scenes. Here's DMNerf again, and you see our quality is much more cleaner than DMNerf or panoptic neural fields for that matter. We also show results with panoptic neural fields, but run with ground truth bounding boxes because that's one thing that's limiting them. So just to give them a fair chance here. But even with this, we show that we're much more robust. And I'll end up with a scan of our office room here, and you get the nice segmentations here. Okay, Matthias will take over from there.
Okay, so most of these results that you have seen right now, they were basically on well, commodity scans, right? So you took some RGB images, you run some 2D segmentations, then you optimize the nerve, and then you kind of jointly get a 3D reconstruction. But one thing we have been struggling, generally speaking, is how do we actually evaluate these methods in 3D? And then even if you're taking a step further, like how would you train like a foundation model on 3D data to begin with? And a lot of people have been doing this on ScanNet. And if I go quickly back, this, in my understanding, is one of the old ScanNet scenes. And you see, you know, the quality is just not as great. And the reason why that quality is not as great is this was captured with a handheld sensor. It was basically an iPad with a structure sensor on it. And the problem with that data was that it's not so great. So how do we get 3D foundation models, right? How can we get there and actually train these kind of things? And this is one thing that we've been looking at for quite a while. So ScanNet we released 2017, which was, you know, like the first large-scale 3D data set that actually had semantic instance annotations. But we thought, especially with these methods, what Javor and so on has just presented, they're just not within the spirit of the time anymore. They're just not the same quality. On the right-hand side, you see what we're currently working on. We're trying to get basically much, much better geometry. And the geometry has multiple reasons why we need better geometry. Obviously, we want to get better semantic understanding. We want to get better features that we can learn from, more detail, more fidelity. But it's also important when you're talking about reprojecting features from 2D to 3D, accumulating features in 3D, that gets a lot better when you have this kind of data. And if you're doing a little bit of a comparison, the problem with the original ScanNet was that the local geometries, they just were so inaccurate. So like just thinking about view consistency and stuff like that, it was very, very hard to do. On the right-hand side, you see some of the comparisons here. You see, like, actually the geometry is pretty fine scale. And also you see that the annotations are on a much higher fidelity because now you can actually annotate directly in 3D, even smaller objects that we couldn't do before. And one specific thing was very important to us is, well, a lot of people have been trying to get Nerf to run on ScanNet. But running this on ScanNet is a challenge, to say the least. And we have to apologize, I guess, in retrospect for choosing such a poor RGB camera, but it was just easy to do at the time. So here on the left, you see basically the iPad Air RGB camera that was 1.3 megapixels. And now what we're trying to do with the new ScanNet version, we're trying to get to 33 megapixels with high-end DSLRs. And the way we chose that setting for the DSLRs, basically, we asked Ben Mildenhall, the main Nerf guy, like, hey, what's the best way to capture Nerfs? And we just duplicated that setup. We took the same Sony camera that he had. We took the same settings. We took the same ISO, everything basically all the same. And we just replicated that. And we tried to get some data. And now what we did is we actually had several modalities. So we had, on one hand, we had the DSLR images that were captured with DSLR. We continue to capture them with burst mode. So when you do that with a DSLR, it makes like click, 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 and it just goes through it. We have a separate test trajectory, so we want to get a benchmark on that. And then what we have is we also have lower end iPhone data. So in this case, we're taking iPhones with RGB sensors and iPhones with LiDAR sensors. So we actually have both. So the iPhone data is not in terms of RGB, but the LiDAR data from the iPhone is actually fairly low quality. And this is very intentional why we're doing that, because now we can register these modalities with the intent in mind to essentially train networks to do depth upsampling, depth super resolution, and combine it with semantics that we annotate, as well as with like few novel view synthesis methods like Nerf methods and semantic lifting methods that combine these kind of ideas. For the geometry, that one I haven't mentioned yet. For the geometry, we taking a Faro scanner. The Faro laser scanner is pretty much the best quote unquote commodity what you can buy. That costs like $50–60K. It's this little piece that you see here. You put it on a tripod, you put it on a position, it spins around, it gets you per location about 40 million points per scan. And then at the end of the day, what we do is we just put this tripod at many locations in order to get more at the end of the day. And finally, we do a lot of pre-processing here, right? So we do essentially the registration between the Faro laser scanners, between the DSLRs, and between the iPhones. So we have pretty good registrations. And the reason why the registration here is really good is because the geometry is so rock solid. So the Faro gives you basically sub-millimeter precision per point that you capture. And this makes like any ICP method or whatever just really straightforward. So you don't have to deal with a lot of stuff like this. Here you see roughly how this registration looks like. So you see here the scenes. You see these local renderings here are camera frustums. These frustums, the dark blue one, they are the training trajectories. So we have a relatively dense training trajectory that you can use for your favorite nerve or semantic nerve methods. And the red ones are the test trajectories. So these ones are independently taken in a second pass, such that we trying to uncorrelate the training and testing trajectories. And then what we do once we have these scans, we start semantically annotating them. And here you're getting annotations that look like this. So if you zoom in here, you see these are the local geometries. You see the semantic annotations. These annotations are done by a lot of undergraduates we hire. So it's quite a tedious job, but we think it's pretty important to get more and higher quality 3D data with annotations like these ones. Okay, so at the end of the day, we're scanning a bunch of scenes. We are currently, we're currently at about 400 scenes, a little bit over, like 405 or so. We just crossed it by scanning our couple of places in Vancouver, mainly SFU and friends. And we have currently a little under 200K DSLR frames, 3.3 million iPhone RGB frames. And we have the respective labels, and labels in this case means they're 3D labels on 3D segments where we have instance annotations. And these ones are pretty high quality because we do several passes with fix-up stages. So now we're trying to do two basic tasks with this data. We have on one hand the whole nerve stuff. We wanted to know the view synthesis. I guess that is pretty critical to a lot of people in the community there, because one weakness for the nerve folks, what happens right now is every paper captures their own new data, and they're capturing it in a way such that the test looks good. And that's not what we want. What we want actual benchmark, meaning that people can essentially run their nerve methods, they upload their results, and we give them a number back and tell them how good it is, relatively speaking, and we never reveal the test trajectory, the ground truth test trajectories. And this, I think, is pretty critical, and this is something that served us really well in ScanNet and made ScanNet a big deal. For the benchmarks here, we have two modalities, right? We have the DSLR and we have the iPhones. And our goal is basically you can use either modality to train, but then the testing is going to happen essentially on the DSLRs, because that's what we consider is to be the actual ground truth. So the iPhone data is not terrible, but this is captured in video mode, so you still have a bit of motion blur. But that's very intentional, right? So we're kind of assuming that a method should cope with that eventually. And then for semantics, we're trying to marry the two things. So now we have 3D semantic segmentations, which is again annotated directly in 3D. And we have 3D instance segmentations, where you have instance labels that distinguish the respective objects and make them consistent. And we already ran a bunch of these baselines. I can't show all of them because we're running probably a little bit out of time otherwise, but I wanted to show you a little bit the type of quality you can get here. So this is a reconstruction that is done with the latest Nerve Studio version that's using this Nerfacto by Metansig and others. And these are the type of environments that we have captured here. We also compare already, so we already have the benchmarks for some state-of-the-art methods set up. We're comparing against the standard, the original Nerf version by Milton Hall et al. We have TensorRef, we have InstantNGP, Nerfacto. And we do this on both, actually. We do this on DSLRs as well as iPhone data at the moment. Okay, with that, I'm going a little bit to the conclusion. So the two works we have presented here was Java has presented his work on panoptic lifting. That's a CVPR paper from this year. The Scanet++ is still under development. So currently we said we had about 400 scenes. In a month or so, we will reach 500. And the goal is until the end of the year, we want to have at least 1,000. So, and then we hope that this will actually be, you know, something that people can use, can train on, and can work on. And I think these two directions, I think they actually go together. To me, what's really missing in the view synthesis part, people don't know about semantics. And I think semantics is really critical to eventually learn some priors, specifically when you're considering like, you know, the analog of like 3D foundation models and stuff like that. And there's one last bit. If anybody here has like fancy Airbnbs or any fancy places, let us know, because we brought all of our scanning equipment. Just shoot us an email. We would love to scan some of your places and add them to the eternal scanner dataset. With that, I would like to thank. We still have hopefully a bit of time for questions, but I also wanted to play the final video that we have right now. Thanks a lot. Question.
How big is the gap between the predicted training on iPhone data versus EDSL?
Yeah, it's so if you're zooming out on a projector like this, it might be hard to see. But if you're looking this on a nice screen, you see it quite dramatically, and especially when you zoom in, the iPhone data actually does have a lot of locally has a lot of motion blur and imperfections, and that's actually a big difference in practice from a data quality. So you can see, like, I think the DSLRs was like 30+ megapixels. That's like pretty much the best you can get. So yeah, I would say there's still quite a difference, and I think it would be really interesting to kind of learn joint super resolution and optimization methods that could actually bridge that gap. Because all the nerve methods that you're seeing right now that produce these flashy results on like Twitter and social media, they are done with high quality DSLR data, but it's very rare that you see low-end data producing actually very good results.
Yeah, and does this like a gap in quality reflect in performance numbers that you
Yes.
recently?
Yes, absolutely. So yeah, so the performance numbers, they are reflected. I should still say a lot of people report things on PSNR for novel view synthesis, and novel views. So PSNR is not a good metric for that actually, for several reasons. First of all, I mean, PSNR is just a logarithmic L2, right? I mean, that's it. And the challenge is, like, L2 metrics are really bad because they don't have a notion of sharpness, right? It's just like how close are you to the respective images, and they have no notion of how few consistent are you actually relatively when you're doing trajectory optimization. So we talked about this actually a lot. Like, there's a few metrics that measures temporal stability in videos. So you could try to adapt these ones, but they're also not great. So we tried that one out, and these ones, they basically focus on very large flickering regions. So you have like a wall or something like this, and it changes the color. That would be a massive difference in a video stability metric. But the problem is, what you would really care about here is like local metrics that are like local small flickers. And that's almost in none of the metrics is that reflected at the moment. And I think, yeah, I mean, a lot of people thought about it. It's just a very difficult problem because it's so perceptual. Like, we humans, our visual system is very sensitive to temporal artifacts. And it's basically none of these metrics reflected. But yeah, so there's a big difference between iPhone and DSLR metrics in PSNR. There's also a massive difference in like LPIPs, KID, and so on, right? But again, take those metrics always with a bit of caution because they might not reflect how the videos at the end really look like.
Couple of more minutes for questions.
Thank you for the talk. And I was just wondering if there's any rules that you try to keep on all of your scenes on the training and test trajectories.
Yeah, so we have a very specific way how we do capture them. What was very important to us is the training and the test is far enough apart. That was really critical because, again, like, the challenge right now is it's kind of a bit of a Wild West right now how people evaluate. So what people are going to do is they know how they want to make a scene look like, and that's the train trajectories they capture. I mean, you can't blame them, they want to publish papers, right? But I think that's not the right way to think about this in the long run. I think in the long run, you want to have more extreme cases, and that should be reflected in how the test trajectories are being used. So the way we're doing it right now is we first go training alone. So we go into a room, right? We scan it. We want to make this as continuous, in this continuous mode with the DSLR, and the test images they're individually taken actually at separate locations. I'm not going to tell you exactly how they look like because we wanted to make this a bit of a secret, so people don't basically over-optimize for that. But it depends a little bit on the environment. I have to say one thing, what was a practical challenge. So we try to capture a lot of, scenes basically that were very cluttered. And cluttered scenes means there's a lot of objects around. So scanning one of these scenes takes about 1 hour to 2 hours. And in that time, you're not allowed to change anything, because if I'm going to trip over a chair and move it around, then I can start from scratch, because then the geometry registration doesn't work anymore. And unfortunately, this influences a little bit how we choose the trajectories, because we didn't want to trip over stuff. And so this is a bit of a disadvantage. But yeah, so we have a very specific way how we do it, and we want to make sure that test and train is separately done in a specific way. Yeah.
Okay, so if I understood it correctly, the training trajectory is not totally random. It can be decided by how the scene is.
Correct. Correct. And for test, we try to spend additional effort to make sure it's more random. If that makes sense. Yeah. I think there was one question here in the back, right?
Yeah, I think we're usually document with like procedural or synthetic scenes, the way to scale up the training and also get
Agreed. Yeah, that's a good question. So, like, can we use synthetic scenes to actually do training in 3D? And generally speaking, I think synthetic data is a really great tool for various tasks, and I think this deserves a lot of research. If you're thinking about scaling up, like, 3D vision in general, it's very difficult to get a critical mass of 3D data. And this is a question of economics. Like, we spend a lot of effort on like capturing these scenes, like, let's say 1 to 2 hours or something like this. But it turns out like hiring an artist and modeling a synthetic scene is at least 2 orders of magnitude more expensive than scanning them, which is insane if you think about it. So we thought about this not here specifically, we thought about this for humans. So for humans, we try to see, oh, can we hire an artist to model a bunch of human 3D models that we can use for rendering them? An artist costs at least $50 an hour, right? For one human, they needed about 20 hours, right? So you're like at least 1,000 per model. And that's one object. Okay, it's a human, it's an important object, but and they were not super photorealistic. It doesn't have any lighting, it misses a bunch of material. And if you're doing this on a scene basis, you're suddenly getting to a place where like one scene is like 5K or so. It's just economically very hard to do. But I'm not trying to say like this is not possible in a sense. Like larger companies tried Facebook tried this replica data set, but they got it to like 18 scenes. And I think they spent like $10 million or so on it. Not quite, I think it was like $7 or $8 million, but still, like the order is very hard to bridge. But I think still synthetic data will be still very useful for certain things, especially to learn like few invariances and stuff like this, right? Because you can generate, once you have a 3D scene, you can have as many images you generate as possible. So I think it's still very valid. The only people, I think, to my understanding, who are using it on a regular basis are the robotics folks, because they have like mostly one contrived scene, which is like a robot, picking up stuff and so on. And for that, it works really well because you don't have to model so much stuff, basically, right? No. Cool. Any last question? Just one more, yeah.
I have a question about your first book.
Okay.
So there is a video version last form. However, it's timed out on the multi-video prediction, and if that have some difference between, because that were considered consistency between different frames.
You mean the video version?
Yeah, the video version.
So one thing we don't assume is that the frames would be in a sequence. So that's a little bit different in terms of like the video models and this model. We just assume that it could be random shots in the scene. So we don't assume the temporal dependence between the frames. So that's why it goes a little bit away from that.
Cool, thanks.
Okay, let's thanks the speaker again. We'll have more time for questions in the panel. Maybe you join the panel discussion. 900 over to we will manage to scope that.
Okay, so our first presenter is Joy from Stanford. She's going to present her work.
I'm sharing my screen. Like if you let me share my screen, I'll present to there. If you connect your laptop there, that makes sense. So now I'm sharing.
You want to use my voice?
Use your laptop to show the screen so I can look at the presenter. So if you just connect your laptop there.
You want to use? Oh, okay. I share the screen.
Yeah. Maybe full screen.
Not personal. Use your own voice or my voice.
Can you use it?
Okay, so hi everyone. My name is Ren Ding, from PhD student from the University of Hong Kong. And today, I'm really honored to have the opportunity here to present our work, a PLA language-driven open vocabulary 3DC understanding. So first, let me briefly introduce the open vocabulary task and our motivation behind this work. So nowadays, the most models we train today are closed set models because they can only test on unlimited classes, the classes that we have seen during training annotated in the training data set. So if we, during inference, we encounter a new unseen categories, our model always fails to recognize it, just as the bookshelf case in this figure. And besides, the annotation cost in 3D data is really heavy, which makes us invisible to totally rely on human labor to annotate all semantic categories in real-world scenarios. So this motivates us to study the open vocabulary 3DC understanding. We equipped the 3D model with the capability to recognize and to localize the new unseen categories during inference stage. Okay, so recently, the large vision language foundation models like the CLIP model, they have shown a strong zero-shot or open vocabulary capabilities since they have been trained on the massive internet-scale 2D text data in the 2D domain. However, due to the data scarcity issue in the 3D domain, we cannot easily realize like the 3D version of a CLIP. So this is the unique challenge for us to conduct the 3D open vocabulary task, and this is the issue we want to address in this paper. Okay, so our main solution is we want to leverage the image modality and the 2D vision language foundation models as a bridge to build an association between the 3D data and the text data. So with this association and the constructed 3D text pairs, we can train a 3D model with the powerful semantic comprehension capabilities to achieve open vocabulary objective. Okay, so to be specific, first we will generate the text descriptions for a series of images aligned with the given 3D data. The caption model, image captioning model here, it is a pre-trained vision language model without any fine-tuning, and the generated caption, it provides a fairly accurate and comprehensive descriptions like the room types, maybe the semantic categories with their color or texture attributes, and even the spatial relationships between the object and the surrounding environment, and etc. Okay, so then we will use the projection matrix or the geometric correspondence between the 3D point clouds with the 2D images to build the hierarchical 3D text pairs. So the first level is the scene level, that we relate an entire 3D scene with one summarized text. The text is obtained through a text summarization model, which is also a pre-trained language model. So the scene caption is simple and effective, but since it only relates to one big 3D scene with one caption, so it may be insufficient to provide the semantic and the localization clues. So we further design the second level, the field level 3D text pairs that we relate 3D frustum of the corresponding image with its image captions to build these field level 3D text pairs. And further to build more fine-grained point language association, we explore the overlapped region or a different region between the two images to obtain a smaller sized point set, and also with a few entity words to describe it, to construct these entity level 3D text pairs. So with this hierarchical 3D text pairs, we finally employ the contrastive learning to enable a 3D model to learn rich semantics, to have a strong semantic comprehension capabilities for our open vocabulary tasks. And this point language association model is a task agnostic one. And to verify its effectiveness, we mainly conducted two fundamental vision tests, the semantic segmentation and the instance segmentation. And our model can outperform the previous baselines by a significant margin. And besides, it also shows us strong transferability on the zero-shot domain transfer tasks. That is, we train the model on scannet-based classes and test on another data set on S3DRS and got a really good performance. Okay, so finally, let me present some visualization cases to show that to which semantic categories our model can recognize. So the first row is the synonymical novel classes. That is, if we input, for example, if we input sofa or couch as the input categories, it can both recognize the right sofa region in the 3D scene. And then the second row shows that it also can identify some abstract novel classes. To be specific, the room types here, like the bathroom or the kitchen, these concepts. And the last row shows that it can also recognize some real tail classes or even unannotated classes in the data set, like the monitor or the blackboard cases here. So it also shows its potential to be like an auxiliary annotator for the efficient labeling. Okay, so that's the end of my presentation today, and this is the QR code of our project page. So if you're interested, you can scan it to learn more details. Thank you. So do you have any questions about our work? Please.
But I think last year there was data called OpenCV. Is it similar, like framework?
So we have a similar objective. Do you want to introduce the difference of our paper?
Yeah, I was just like curious. I'm not an expert in this topic, but just curious. What are the differences between your work and that?
OpenCV, this paper actually has a similar goal as our paper to achieve open vocabulary or zero-shot capability. But OpenCV, it mainly utilizes the 2D dense prediction network like the LSEG or OpenSEG model to achieve a really good semantic prediction on 2D and fuse it to 3D or distill latest features to 3D. But our paper explores to directly learning on 3D data, not depending the dense prediction, dense predictions on 2D data. We want to explore the potential to learning on 3D data and to see its potential. Yes, and I think our two works are orthogonal because we learn mainly on 3D and it mainly depends on 2D. Yeah, so the combination of this modality actually will be a promising direction, I think, to boost the performance on the 3D because 3D modality and the 2D images, they have their own advantages respectively. Thank you.
I think all the papers that are presented here are CVPR papers. So maybe you can also, you have an opportunity to interact more with the authors in the photo session of the next one.
Okay, and our last presenter for the oral paper session will be Konstantinos Tertikas, and he will be presenting his PartNev paper.
Okay. So thanks for inviting me. We're happy to present our work generating part-aware editable 3D shapes without 3D supervision. Our main interest lies in generating part-aware 3D objects. But why do we really need parts? Let's imagine a shape editing scenario where a user needs to make local changes to the shape and appearance of an object and in different regions of it, such as applying rigid and non-rigid transformations on specific areas, changing the appearance of a part, or combining parts from different objects to form new objects. It is clear that parts are essential when local control is required. Existing nerve-based generative models are able to extract high-quality 3D meshes while only requiring 2D images for training. However, they do not offer explicit part-level control. Part-based generative models do offer explicit part-level control, but require 3D supervision in the form of occupancy labels and aren't capable of generating texture. We propose PartNerf, the first 3D part-aware generative model that can perform local shape and appearance edits and is capable of being trained using only posed 2D images and object masks. PartNerf is a method that decomposes a 3D object into M parts, each being parameterized as a neural radiance field. Each part consists of an affine transformation defined by a translation and a rotation matrix that map a point X to the local coordinate system of that part. We also augment each part by a scale vector that defines its spatial extent and two latent codes that capture the shape and geometry of that part, the shape and texture of that part. We employ two separate networks, a color and an occupancy network, that conditioned on these latent codes, these per part latent codes, predict the occupancy and color values for a point. As we are interested in editing local parts, we want to enforce basically that the parts are contiguous and in local regions. For that reason, we multiply the predicted occupancy function with the nexus-aligned 3D ellipsoid occupancy function. We adapt the NERF rendering equation by a per part rendering equation, where for each ray, we predict a per part color. Okay. So we want also distinct manipulable parts, sorry about that. So what we want to do is we want to enforce a hard assignment between rays and parts. What we do specifically is we associate a ray with the first part that it intersects. We define the rays associated to a part as the set of rays that first intersect with that part. And the color for array R is predicted only by the assigned part rendering. Note that if a ray is not assigned to any part, then the background color is being rendered. Okay, so now let's have a look at the PartNerf architecture and how we can generate 3D objects. So as input, we are given a collection of posed 2D images and object masks, and we train a separate model for each semantic category. To generate new shapes, we base our model to the autodecoder architecture. And what we do is we sample separate shape and texture codes. We feed these codes to the decomposition network that, given the input latent codes, predicts per part shape and texture codes. Given the per part shape code, we predict the pose and the scale of that part. Now, to render a new per part rendering, what we do is we sample points along the rays and we transform them to the local coordinate system of the part. Now, the neural rendering module takes these transformed points and predicts a per part color and occupancy value. We use volumetric rendering to render the per part rendering. Now, we repeat this process for all parts, and we render the entire generated object image. During training, we optimize using an objective function of 6 terms and 2 regularizers. The reconstruction and mask losses enforce color and mask consistency across the rendered and the ground truth values. The occupancy loss further refines the object boundaries and is essential for the hard ray part assignment. We also introduce a few losses for better editable parts. One of them is the coverage loss that makes the parts be distributed along the object. The overlapping loss that enforces non-overlapping parts. And the control loss, which basically says that the parts should be equally sized for better editing capabilities. The regularizer terms basically are constraining the latent space to be normally distributed following other autodecoder-based methods. Now let's check some results on nerf-based generative models and part-based generative models. We compare them in ShapeNet categories, and we showcase better results when comparing to better or on par results when comparing to volumetric rendering-based approaches. Note that these approaches do not offer explicit part-level control. We report the results on the chair dataset and on the car dataset. Now we compare with part-based generative models, and we showcase better performance on the airplane category and on par performance on the table category. Note that these methods require 3D supervision in the form of occupancy labels, while ours doesn't. Let's now check a bit of the editing capabilities of our method. Here we train our network on the Lego dataset, and we showcase scene-specific edits. What you can see is novel view renders of the original and the edited shape. You can also see some results on ShapeNet, where a user can perform translations, rotations, and other operations like texture editing, colorization. And of course, this is possible by directly selecting the partner parts and editing them. Our decomposition method basically allows combining different shapes and forming new shapes by mixing them. Here we show an example of shape mixing on a ShapeNet chair, where we select the highlighted green parts from each shape, and we either combine only the per part shape codes, only the per part texture codes, or both per part shape and texture codes from the two shapes. We also show some shape generation results. To sum up, we present PartNerf, the first part-aware generative model that parameterizes parts as nerfs, is able to produce local control, intuitive local level control results and have numerous editing capabilities, and it's trained without explicit 3D supervision. Some limitations are that the quality of the generated textures could be improved, and the generated parts are not necessarily semantic. Thanks a lot for your time and your attention. You can check our project page and come visit us at our CVPR poster session. Any questions?
USB-C is fine.
Yeah. Cool.
Now we're gonna, for the remaining, that we don't have, I think, by no means that all the papers that actually we selected are, we think is, we believe that they are among the best papers, because we have a limited like space to fit in all the books. So we're gonna have just some small spotlight, 90 seconds or something. And if you're interested, please stop by the like the posters in the poster session by
Hello, so today I'm using 3D utilizing routine on 3D. So the sort of idea of our task is like given some force mesh, where would you put a necklace or some other unrelated category? So how about
Okay. Nice. Can everybody hear me? Let's check that first. And can everybody see my slides? Okay, great. So thank you for inviting me. Like Mohammed said, I'm Angel. And yeah, and SFU is very close. And so if you guys ever want to visit, let me know. So today I'm going to talk about 3D data sets for composable interactive environments. And this, I think I'm going to mention some of my work, but in some ways, this is also just about what I think we should be doing, or one direction. There's lots of exciting things happening. So I work at the intersection of language and 3D representations. And I'm interested ultimately in basically being able to have use language to control helpful AI assistants who can help us around the house. And in order to do that, I'm also interested in building these large-scale interactive environments so we can test different algorithms and methods for these agents. So this is just a list of topics that I'm excited about, ranging from grounded language understanding to, I guess today we also heard talks about open world vocabulary for detection and reference and various other things. Today, I'm not actually going to talk about any of that. I will be giving some talks tomorrow as well, where I will talk a bit more about grounded language understanding as well as content generation using text. So if you're interested, come to my talks there. Today, I wanted to talk a little bit about compositionality in 3D and 3D data sets. How did I get into 3D? So I did my PhD at Stanford with the NLP group, but I got to know some graphics friends. And there I got introduced to the idea of that maybe it would be super cool if we can generate 3D scenes or 3D shapes from language directly. And I have to say, it's an amazing time right now because this was back in what? Was that like 9 years ago, 10? Oh, that was a long time ago. But at that point in time, it seemed kind of almost impossible. But now we have this surge of interesting text to 3D, which is quite amazing. I wanted to talk a little bit about my early work in text to 3D scene generation, mainly because this was kind of a very structured and compositional approach. So the idea here was that if we had a sentence like there's a room with a table and a cake, and there's a red chair to the right of the table, what we would want to do is to be able to parse the sentence and to extract out explicit constraints that are specified. And the idea is that this text, it basically describes a space of possible worlds. And what it describes is constraints that you want to satisfy, but there could be implicit other implicit constraints or relationships that are not specified. And so what I did then was basically represent everything as what you would potentially call a scene graph, and basically a little graph where the objects at the nodes, relationships at the edges, and attributes unary edges. And again, the idea is then you can maybe take this little graph and then infer what additional relations and attributes there could be. And I call that an inferred scene template. The name scene template because you could potentially generate many scenes from it. And again, you have these inferred objects and relations. And this would give you another word you could use for this is a complete semantic scene graph. And I use the word semantic scene graph to differentiate this with this older term of scene graph. For people who are actually in graphics, you're probably very familiar with the term scene graph, which is a little bit different from the scene graph of vision, where you would have this node, and each node would have some piece of geometry, maybe it's just a dummy nodes, and then you would have this hierarchical organization that tells you the transforms of each of the nodes beneath it. And that would then tell you the position of everything, of all the geometries in your scene. And so the idea is then we can take the semantic scene graph, translate it, figure out what the layout should be, and go to this geometric scene. And then if you render and view it, you get this beautiful 2D image. So this was kind of my work back then. And I think there's some good things about it, some maybe not so great things about it. Some good things about it is that it has this, it does follow this compositional approach. So where if you wanted to change, say if you wanted to replace a chair with a different chair, you would just replace maybe some of the attributes. And if you wanted to move chairs around, if you wanted to move this chair from the left to the right, you would just, replace that spatial relation from right to left or something like that. So there's some advantages, but at the same time, it's kind of, back then it was kind of, there's all these stages that can go wrong. And how did this work? It relied on different modules for text to 3D object retrieval and learned shape scene priors. Nowadays, if we were to do text to 3D object retrieval, we would use joint embeddings and we would embed, retrieve. So I'm gonna talk a little bit about how we got these scene priors. And at that point in time, or maybe even now, what we want to do is we want to learn these scene priors. Basically, by scene priors, what I mean is how are objects commonly arranged? Do you put chairs in a row? Do you put chairs around the table? Do you put, chairs upside down? How is it typically arranged? And we can get this from a scene database. And we also kind of assume that there's a 3D model database that we can search from. And so from the scene database, we can learn something I call a spatial knowledge base, because it has knowledge about where things go, what goes on top of what, and what maybe right means. So from this, and the key observation is that, and why could we do this, is because in the 3D scene data sets we work with, they were essentially compositions of 3D objects. So the 3D scenes themselves would basically tell you, this object is this place, and the chair is at this location, the table is at that location, and from that you can just learn a lot of information. But at the time, the database we worked with was very small. It only had like 130 scenes. And when I say, and sometimes in my talks, I will use this word scene to mean two different concepts. One could be a whole house, and one could be a single room. These things are mostly single rooms, so that means 130 rooms. And with that, we would learn priors like this. We would learn like, where do objects go in an office, or where does a lamp go? Like, does it go on the desk? Does it go on the nightstand? Does it go on the rug, and so forth? And for the floor lamp, then maybe it goes on the table. It doesn't go on. It basically just goes directly on the room. Versus table lamps tend to go on desk, so forth. But you can see these are very, very sparse because the data is so small. So because of that, I felt it was important to have larger data sets, and also to have, or maybe at the time, maybe an organized set of shapes from which I could retrieve. And so this is how I got into 3D. And from this is, I've been doing work with a lot of different collaborators and just getting scene data as well as shape data. And this scene data, currently I show mostly scanned data. And these are also all static scans. So recently we had this effort to, instead of having static scans, to try to have scans where you can actually interact with. And so this is a project where we actually went out, took scans of different 3D environments in different articulated states. And then we actually went and annotated not just the objects, but also their parts and how they moved. And this allowed us to create this data set with articulated objects. And you can see that, you know, in the, on the left, is that the left? The left there, is that right? Sorry, spatial relations is part. On that side, where the big picture is, you can see the cabinet doors opening and closing, but you also see there's no inner surface. So there's still a bit of work to do completion to make this complete. But at the end of this, what we got is we got about 100 or so environments with, and again, we would scan these environments at different articulated states and with about almost 10,000 objects and 4,000 articulated part. So this is a project called Multiscan. If you're interested in using it, please let us know. And there's also a website. I think I showed it in the previous slide. But that's still very small. It's like 100 or so rooms. That's extremely small. So the recent static sync data set we worked on had 1,000 houses. That's houses. That's multiple rooms, like maybe 5 to 10 rooms per house, or even more, or even 20. And so you can see the scale is very different. And then if we look at the images, we're looking at 100 million images. So we're very, very far in the terms of how much 3D data we have versus how much 2D data we have. And especially if we look at how much 3D data we have that you can actually interact with, or you can have drawers that open and doors that open. So we really want to see, you know, how can we get to this large scale interactive environments? And I think we really do want to leverage several different things. We want to leverage the idea of compositionality, and we want to leverage all the advances that we've been making. So this is not really a new idea. I think it's an idea many people are familiar with, but to have some maybe initial small amount of, say, annotated data, and then we'll be able to learn to segment and parse, and to be able to then learn better generative models that allow us to create more things. And let's look at this a little bit more. So here I have like 4 points of what I think we should be doing. We should leverage recent advances. This, I think I was here for Matthias's talk. I think he's already doing this. And so we want to leverage recent advances in improved capture. We want to have better quality spaces. And in Matthias' talk, he also talked about not just using more advanced methods, but also just using better sensors to capture spaces that are with higher quality sensors. And yeah, and also we want to handle these certain kind of objects are very tough for traditional sensors, such as mirrors or thin structures. We also want to make sure that we are looking into algorithm and techniques for handling those. And at the same time, I think it's very important to continue researching handling dynamic objects, because often if we want to have something that we can interact with, we want to be able to open a door or open a drawer. Ideally, we want to be able to, for multi-scan, what we did is we took static snapshots. So ideally, we want to have somebody just open the drawer in a video frame and just be able to capture that versus this static capturing. Yeah, and for, I guess I separate dynamic object versus interactive object a little bit in the sense that sometimes the objects we interact with may be a little bit simpler than free-form dynamic objects like a cat, which is very flexible and deforms, while some of these common objects that we interact with, even like the laptop that I have, it's rigid, it has rigid parts. And so there could be like simpler, different methods that are more specialized out those. And in addition, we would want to be able to do like leverage all the advances that has been happening in 2D. 2D semantic segmentation, instant segmentation is just much better. And also it can have all this different data. Like I said, like for 3D, maybe we have 1,000 houses. 2D, they have 100 million images they can train from. So we want to leverage these 2D advances. And maybe we also want to use it not just in the, maybe I call it in the internet setting or just from existing data sets, but also in this embodied setting where potentially, you know, maybe we took a scan of this environment, but maybe our little robot, or maybe we want a very complete scan of the room, and what we want to do is the underside of the chairs. And in that case, if we have a little Roomba robot, its natural viewpoint will be underneath the chairs, and it will have a different kind of representation of the world. Because, yeah. So, and the last thing we want to leverage is pre-trained vision language models. Maybe it can also just be pre-trained language models, but I think there's a lot of work in this, so I won't talk about this too much. Okay, then the next is leveraging synthetic data. So in my initial picture, I had like little scans here, but I really do think we can make use of all the synthetic assets that people have created. And if you do maybe I use the term embodied AI, that's kind of a wider term for people who want to study agents that take actions, but may or may not care about real robotics. If you look at them, they often use synthetic environments for interaction. And why is this? They do it for several reasons. One is that it's just like I mentioned at the beginning, it's just really hard to have like real world scanned data that actually have is articulated that you can interact with. And synthetic data really offers a lot of different advantages. It can have high visual quality in the sense that there's no missing surfaces. It can be modeled such that there's an interior, it's complete. If you take a scan of an object, unless you're opening the drawer, doing things, you don't know what the inside looks like. You're just taking the scan of the outside. In addition, you can also, people do very careful modeling of small objects, so they can be very high fidelity. And the most important thing is really it models various interactions. Like for instance, objects can be modeled with their articulation parameters, like the drawer comes out, the door opens, or the lamp neck flexes. And in addition, you can have lighting changes as well. You can say, here's where the light is, and this is these parameters, physical parameters for different light settings. And conceptually, it's also easier to get ground truth semantics. I think we'll maybe talk about that a bit more. However, there are disadvantages in the sense they're quite expensive to create, and each effect. So if you wanted to have something that's articulated, you need to, or somebody needed to be able to actually model that in that object. So it can be quite expensive and requires a lot of effort. And a lot of times when people are designing synthetic data, they don't really care about physical realism in the sense that they just tweak parameters. So there is this concept of, I guess, in graphics of physically based rendering. However, it's still in the, even so the technique for maybe doing the rendering is physically based, the actual parameters are often just tweaked by artists so that it just looks visually good. So does it actually have a physical meaning? It's also somewhat unclear. And often these synthetic scenes are often also just not as cluttered as real world scenes, and some details can be missing. But still, I think synthetic data, despite its disadvantages, is very useful. You can always mix it with scanned data. There's nothing to say that you can't have a mix. And you can use this data as a prior on what object structure looks like and what the scene layout is. And I would say the biggest advantage of synthetic data is that it's easy to compose. So if you take a scan, right now, sometimes maybe it's incomplete, but again, if you take a chair, even if that chair is pretty complete, if you were to remove the chair, then where it sits on the floor, it would be not seen, and that will need to be completed. While synthetic data is just the floor would have been already modeled as being complete. So it's very easy to compose with it. Just as a reminder, we want to leverage compositionality, and we know that objects are composed, environments are composed of objects, and these objects, you can take the same set of objects and you can just rearrange them and you can get a completely different layout, and that gives you a lot of diversity and variety. And then the next thing that I want to say is that objects are also composed of parts. So if you can have parts, if you understand what parts they are, you can actually use them to form a combination of different objects. And if we look at the idea of, so now we have objects and we have parts. So now if you start to take an object and if you put them into scenes, what happens is that you can have one 3D asset and you can have all kinds of information associated with it. You can have the semantic category, you can know what the parts are, you can have rich articulation information, you can have, what material it is made of, you can have all kinds of information. And any scene that's using that object would already have that information about that object. So it would basically just propagate. And that's what we kind of mean that ground truth is kind of easier to obtain in synthetic data set. And if you just then take these objects and rearrange them and potentially retexture them because they could have different materials, then you can just have this very, very rich, diverse set of new things. And people have actually done this. I don't have a slide for that, but there's this paper called Poxor presented at New RIPS last year that showed that if you can actually synthetically generate these arrangements of scenes, and it's actually very useful for embodied AI. We've been working on, this is in collaboration with Meta and Georgia Tech. We've been working on this data set called Habitat Synthetic Scenes dataset. So Habitat is a simulation platform that allows people to do kind of embodied AI experiments where you can have robots that go from one location to another location, and maybe robots that pick up things. And the HSSD is basically 211 houses composed of 18,000 objects with roughly 330 object instances per house. So what this means is that the 18,000 objects are kind of unique objects, and then some of the objects will be repeated because we're reusing the assets. And we have 211 houses. You may think it's not very many things, is that? But these are multi-room houses. So each house probably has like 5 to 10 rooms. So you can multiply by like, say, 10, or, if conservative side, multiply by 5 for the number of rooms. And that's how many scanned scenes it will be. So we're quite excited about this data set, and we're using it for a variety of different things. You can look at the website for more information. And again, we do have, it's composed of over 18,000 different objects, currently categorizing to about 466 categories in a hierarchy. And you can kind of see the variety of objects we have, the different kinds of wall lamps and so forth. And currently this data set does not yet have, you can't interact with objects, but it is on our roadmap to make it articulated. So you can actually have these 211 houses where you can have interactions. Okay. So I've also said that we do want to have part level understanding. And so this talk is most about data sets, you see, it's about data sets. So for part understanding, we have like PartNet, this is from a while back, where you have this PartNet data set where annotators painstakingly annotated each part, including these fancy chandeliers with many, many parts. And this is just showing that they did this for 26,000 ShapeNet object, and it's like tons of parts. And this is a hierarchical part segmentation. So, so depending on your level, what level of interest you have, maybe you only care about the fact that this is the back of the chair versus that's the front of the chair, or the seat of the chair. You don't care about the metal slats, or maybe you do care about the metal slats. And so it can be used in different ways. And based on that, and also a subset of the models, maybe augmented a bit, was also annotated with mobility information, including the type of motion, the axis and origin of motion, and range of motion. So this is what it looks like. And again, this is going back to the idea of articulating things. So with this kind of data, then people can start to do projects, and people have been doing projects. I don't really list all of them, but you can then use this data to do projects in predicting the mobility of how things move. So here's an example from my group that where we did, given a single view image, try to predict what parts open and close and their motion parameters. And the idea for this is that this could be very useful for robots that need to understand, okay, maybe this drawer can, if I were to open it, would go this way, and maybe then I shouldn't be standing right there. Maybe I should be standing to the side of it so that it can open. Or it could be, if we wanted to, again, if we were actually want to grow our data set of things that can be articulated, then we can then potentially use the same method on things that hasn't been articulated to predict what how the motion is, and then potentially create more data. Again, this is just so this work was presented at ECCV last year. And basically, again, we take a single view image, predict the parts and what the motion parameters are. And the parts we're interested in, we only care about 3 different parts, and that simplifies the categorization very a lot, that we only care about drawer, door, lid, the things that can open. So this is all very exciting, but there's, I would say, a lot of challenges still remaining, and there's a lot of things that are missing. And so this is an open challenge, and I would encourage anybody who's interested in this, understanding objects more. This is things that you can work on. What materials go on objects. There has been some papers, some work that do this in the sense that, okay, here's an object, what material can I, high quality material can I put on it so that when it renders, it's very beautiful. But there's other things like physical properties, such as, the mass, how heavy is it? Where would the center of mass be? What does this object sound like when it's struck? And different affordances. And again, people do research in this area as well. Recently, there's this work called the Object Folder, where they connect different modalities of information for this. Okay, we should wrap up. But again, the idea is that once we have these objects and we have these, we have a database of scenes, then we can learn models that can allow us to arrange them into new room layouts. This is a work from 2018. This is in collaboration with Kai Wang and Daniel Ritchie at Brown. And the idea here is that we would basically auto-regressively figure out what objects should be added where, and then basically form a top-down view and then add them into the scene in order to create a scene. And here's just some examples of the kind of things you would get. Since then, there has been quite a bit of advances. And maybe even before then, there has been some things that my old work was capable of doing that previous model couldn't do, in the sense that the old work will basically leverage this idea of support structure. So you could figure out where would things go, and they could basically put things on different surfaces. And this is an example of the text to scene system that I started my talk with. But since then, I guess this is actually also work with Kai Wang as well. But you could also do scene generation, where instead of doing this top-down auto-regressive layout, you could structure your scene, represent as a graph, and then use that to figure out where things would go. More recently, other people, I'm not involved with this, have been using transformers to, again, predict where objects would go. But all of these methods, you can use them potentially to just generate huge, potentially data sets of 3D scenes that you can use for different purposes, maybe to train nerves, maybe to train your home robots, different things. Ultimately, we would also want to go beyond a single room. So we have done some work where we take these floor plans and we create these the architectures, 3D architectures for the based on the floor plan. And then you can imagine then taking each of the rooms and then populating them with furniture. And another way to go beyond single room is to maybe potentially even take these existing scans that are only one rooms and then somehow glue them together. And if we can, so far I've been talking about, when I talk about scene generation, it's been mostly about, okay, I have a database of models, I retrieve it, and I figure out where it should go. I have a layout and I put it there. But again, nowadays, there's a lot of interest in generating 3D shapes directly from text. So instead of retrieving a model from a database, we could also just directly generate a 3D shape or chair instead of retrieving. And again, however, there's a lot of open challenges here, especially with regard to interactable objects. I don't know who exactly, maybe, okay, there's a lot of people who are doing 3D to shape generation. So I'm sure there's somebody doing interactable object generation, but maybe relatively few. Anyways, I would like to conclude and summarize and repeat that 3D things are a composition of objects. And if we should model environments as objects as part, and then if we can learn to parse objects from the environment, then we can slowly learn the generative model that will generate these things. And yeah, and this is pretty much my talk. Thank you for listening.
Thank you. Sometimes the question.
Questions? No questions.
I think Matthias just talked about the advantage of real data compared to synthetic data. So do you have other comments to say? For example, what's the advantage of synthetic data over real data?
Oh, yes, I guess I did have a slide on that. But I do think the synthetic data is actually so Matthias is trying to capture real data. I do think there's value. I think there's value in both. Shall I say that? There's value in both. And I think we should be continuing on both fronts. But I do think synthetic data, especially if you want to do things that involve interaction, it's just much easier to work with because it is more complete. And if you wanted to do people talk about, oh, it's very expensive to collect, it's very expensive to create assets, 3D assets. It's true. It's true, but at the same time, there's a lot out there. And these companies have money. They have money and they can buy the assets. And some of them are willing to, I didn't quite say, but some of them are willing to, I don't know how much HSSD costs, but it costs some a bunch of money. I don't know how much, but they want to see research with, so now they will be open sourcing that. We will be open sourcing that. And if you listen to Matthias, he also said, you know, for this, it takes a lot. It takes 1 hour to scan a room. And that, you know, Matthias, how much does Matthias get paid? I don't know, but maybe he can get paid $1,000 an hour, and it's maybe Matthias plus Angie. So I don't know. And then there's the post-processing. So can be quite expensive too. Okay, we can talk more about that. Other questions? Yeah. Question in the back?
Reading content communication, things like that. Do you see this as, I haven't used it personally, but I think I've seen it out there. So do you see those tools, Letter, Regina, able to recreate maybe thousands of different variations of
Yes. Yes. So I think that's the other thing that's going to happen. I don't know. I will say I don't know too much about Omniverse to start with, but I think what you will start to see is that once people, so if you think about where did the 2D images come from, why is it 100 million of them? It's because it's so easy to create them, right? You just take a picture, you just press your button and you get that. And but creating 2D art used to be hard. You have to artists slowly go at it. But now there's like diffusion models. And so what happens is that if I wanted to create a custom picture of like, you know, like I guess there was a picture for a squirrel riding a skateboard, that maybe before it would be very hard, but now you just type into the text and it's there. The same thing is going to happen with 3D in two ways. One is that these companies, I don't know if necessarily Meta or NVIDIA, they will be among the players. Some of them will want you to pay for their services, right? But then there will also be companies that will just let you use it for free. And then what you're going to see is that you will be able to create, you know, these new 3D objects very easily. And then they will enter the ecosystem. And at the same time, what is Matthias doing? He is trying to do these, make it, okay, he's not currently making it easier to scan, but ultimately so him and people like him wants to do is make it easy to scan so that you can also take your scanning thing and just go, phew. And I think also even now, like scanning things is hard, but even now, if it's a small object, you can pretty much, you know, take your iPhone or whatever, there's apps, you can scan it and you can upload it. Yeah. And there's also, I should say there's also just recently this other, I didn't mention this, but this thing called Objeverse that has, I think it came out at the beginning of the year, which is a core of, I think, Sketchfab, of a whole bunch of 3D models, and they are of varying quality. Some of them are good, some of them are not so good. Question?
So we can have actually the question on the way. Continuing that, just I asked the.
So I will stop sharing.
Yes. Just, we're gonna continue with the question and see the full discussion.
this topic. Could you please? I'm gonna ask some questions. This is gonna be the discussion, and then we're gonna start with some general question or open question from myself. I want everybody to answer to those questions one by one. Hopefully arguing with each other, that's also fine. And then after that, this will be the microphone where you guys can line up and then ask your own questions directly for a person you are interested to have answered some of those questions. So the very first general question, and I want to start maybe from right to left to answer, is like, what is the biggest and most important key challenge in data generation for content understanding? And let's please start.
The biggest challenge.
Yes.
I think one thing is evaluation.
Could you try to speak to the microphone? It helps actually for the Zoom.
Okay, so one of the biggest challenge I think for content generation is evaluation, in the sense that how do you know what you've generated is any good? Is it useful? Is it different from what you've done? What people have? So would it be valuable? So I think that would be mine.
So what are the questions? Second part is try to answer your own key challenges. So what would be the answer for your challenge? How would you tackle that?
Oh, how would I tackle that? The evaluation?
Yes.
I would try to set up some evaluation metrics and then decide on, what is missing. I guess even I keep going back to Matthias's talk. Sorry, I have to apologize. I was not here for everyone's talk, but Matthias' talk was here, and anyways, one thing he's trying to do with his data capture and with the ScanNet++ is to establish a benchmark where NeRF models can be evaluated, right? So I think to start with, for content generation, I will also have to admit it's very hard to keep up with the explosion of work. So maybe some of what I'm saying is already old, but some of the earlier works, such like, for instance, Dream Fusion, like the way they evaluate is not the best. They don't really evaluate necessarily, but some of them don't necessarily evaluate the quality of the 3D very well. And I think even the way they evaluate the match of the 3D to the text is not very good. So that would be where potentially I would start.
Thank you.
Okay, just to be clear, I understand the question. So content generation for what? So you want to make 3D assets for what reason?
That's also a good question.
Like for games or for robots to play with them? Like that's what I'm wondering.
Yes, whatever you like, what is the most important
Okay,
for you?
So thank you for leaving me open. So I'm very excited about this problem. We just have a work under submission, we call it Gen to Sim, generative models to 3D, and this specifically for robot learning. So this is for Coral, where we look at images or we look at the articulate models that artists have done, and we try to lift them into 3D with the purpose of having us play with them and learn policies that actually can generalize to the real world. So just scaling up robot simulation using latest generative model, like progress in generative modeling. So I think this is very, very valid, like trying to get explicit simulators fast. Yeah, there's a lot of challenges. The main challenge is we don't care about static things, we care about dynamic things, how things behave, for example, laptops. So in that case, to really do simulation, you need to understand videos well, which is actually an open research problem. And the way to address this challenge is, I think we really need to continue pushing on video perception, spatial temporal reasoning, and so on. The better we can get out of a video, the better we can create the content and physics and how it behaves.
Oh, are we all answering?
Yes.
Wow, okay, got it. Okay, so the question was, what is the impact of, how would you go about data generation? Is that the...
So what is the biggest challenge that you foresee?
Okay, I think I get the question. So I think the biggest issue right now with 3D understanding, and that is definitely very valid for NeRF, is generalization. Actually taking a model, let's look at 2D. Let's look at where 2D is. You have a model, you apply it to some image, you're not thinking about what image it is, it just works. None of this works in 3D. So before we're going to talk about asset generation and generative models, we haven't solved a very big problem in 3D, which is how we're going to build generalizable systems at work. So I think the biggest challenge is going to be how we're going to achieve that. If data is going to play a role in it, and I think that we know that. So what I would do for data generation is I would try to generate data such that I can build generalizable systems.
Thank you.
I'd say like if you've seen like the content generation that's been going on in 2D, like that's facilitated with how much content we already have in 2D, right? Like all these nice models like Midjourney and all that. Like there's so much art on DeviantArt and like all these platforms. We don't have something very similar for 3D, right? Like there are data sets coming up, right? Observers, but like if you look at it carefully, like I think you have to manually go through the assets to actually like filter out what's usable. So I feel like data generating, like getting the data already to train these models is like a really important part. And like Matthias was talking about the ScanNet++, I mean, that's definitely a step in the right direction about the, like high quality data collection, but like we're far from where 2D is in this aspect. And like we see that we have to work on these smart algorithms for like 3D generation just because the data is not there, right? Like you have to compensate for that with smarts in the algorithm side. So I feel like the challenge is more around the data side. Like we really need better data sets, I guess, more data.
Thank you.
All right, let me first introduce myself. I didn't speak before. My name is Peter Wonka, and I'm a colleague of Mohammed. So one challenge that we always face for generating the data is the huge cost of the data generation, and in some sense, the uncertain quality. So whenever you talk to someone about a data set and they're unhappy about the quality, they say, "Oh, this data set is not good, maybe wish higher resolution, or it's too blurry." And so it seems that you spend a whole lot of money and effort to generate the data set, but maybe you didn't pick the right camera, as it turns out afterwards. There are data sets that capture the nerves, but then maybe the individual images are not good enough. You actually can't get the nice 3D reconstruction you were hoping for. And then you sit on 20,000 captured objects, but you just didn't go high enough on the scanner, or maybe the good scanner isn't on the market yet. And I think somehow just getting the quality at the level you need is the real tricky part, because you don't really want to commit to this huge effort, knowing that the quality is going to be a problem now.
And how would you tackle that challenge?
This, unfortunately, I don't really know, but I think that this is just inherent. I don't know if this is really solvable.
Sounds good. Thank you. All right.
So I also do like very much the generalization aspect that Georgia has referred to. This is, I think, this is quite exciting. And building data sets that inform generalization research is, I think, is a quite tricky question. For example, when I would hope one day to have models that can generate shares that have the understanding of the level of details of what material should associate with every class that fits a specific living room that I live in. Maybe the 3D vision research is not there yet, or far from maturity from understanding these particular aspects. We do have models that struggle on recognizing even a set of, let's say, handful of materials or something like that. This often gets even more severe when we wanted to generalize on thousands of categories. I'm not sure what Georgia refers to in terms of the scale of generalization. Is it at the category level? But I think most of the existing data sets in 3D have maybe tens or to my knowledge. Maybe I'm not quite sure about I might be ignorant about all the aspects, but I feel it's in the scale of tens. And when we refer to generalization, what do we really mean? And when we think about building data sets, so that informs generalization, what are the steps that we should do while we collect the data to
to make this evaluation set measure the right thing.
Thank you. The next question would be like, with a similar from everybody, how to get a strong general 3D foundation model, and what data actually required for that. So many times 3D foundation model actually was mentioned actually during the presentations, but there is no 3D foundation, very strong good 3D foundation model yet, or image or content generation, 3D content generation. I would like to know your opinion how to get to that level and which data is required for getting a good 3D foundation model. Let's start again from you.
Oh.
Yes.
So I haven't tried myself on any 3D foundation model, but I think in order to build a foundation model, I think one thing to say is that maybe when we do the 3D, we can leverage everything that other people have learned in 2D and in language. So there, maybe we can have a little bit of a boost. But so far, like what do we see in language is that they need to have scale. They need to have a lot of data. So there's a question of, for 3D data, do we need as much data, or can we leverage some of the 2D information? And if we can leverage 2D information, maybe we don't need to have too much 3D. That I don't know. But the other thing is they need to have compute, right? Compute, and I think, I think there's companies who are already building these 3D, maybe trying to build 3D foundation models. I don't know if anybody here is affiliated with any companies at this point. So I would imagine like there's companies who are trying to do that. Maybe Hugging Face, I don't know.
Yeah, so 3D foundation model, probably you envision a model that goes from an image to 3D, or what do you envision? Or a model that consumes static multi-view videos taken from static scenes. Is this what you mean?
As you request, any of those event.
Yeah, so I don't think that the separation between 2D and 3D is so much. So I've been working on 3D for very long. I don't think it should be considered separate. And I'll give you two examples. One example is people, for example, try to use 3D point cloud and 3D architectures to predict actions for robots. And they just start from RGB point cloud. They don't use pre-trained features. But it turns out you can just use image features, leave them in 3D, and just use them to process actions, and you're going to do much better. We're working on a project where exactly the same architecture is used, whether to process single image or 3D. And the only thing that differs is the positional encodings. In one case, you use 2D relative attentions, and the other case, you use 3D relative attentions. Of course, this assumes that you have also the pose, but pose can also be predicted on the fly. So I really don't believe that these are different. The reason is that humans also use just monocular perception. They have two images, but also the stereo blind people, they don't have any problem. And there are very few people that are stereo blind, then they acquire stereo, and they say, yeah, I can see the objects a little bit more separate, but it's not that they couldn't pick up a plate before and then they managed to pick it up. Do you see what I mean? So that's number one, that I think that like 2D and 3D are super, super close. And the second that supports this opinion is the immense revolution the last few months on 3D generation coming from generative models. In Kazin workshop, like down the hall from the east side of this convention center, I just saw whole courses, 3D articulate models of forces being inferred from a 2D diffusion model of forces. Okay, like it's called 3D farm, to be shown in this CVPR 2023. So I do believe that actually completely in contrast to what you said, that yes, the whole point of actually even computer vision perception is get 3D from 2D. We shouldn't be trying to get 3D data sets to get that, because this is part of the whole research and algorithms and so on. But again, this is what I think today, like tomorrow I may be completely different. Thank you.
Thank you.
Okay, I have to say something else. So I guess the first thing I want to say is that I feel that as a community, especially the people working on 3D, we need to be a little bit better in defining what is 3D, because 3D is a huge term. It is much bigger than 2D, and I'm serious, it's a single object, it's in multiple scenes. Do you assume a 3D sensor data? Not, what is the task? It's a big, and then I talk to my colleagues that are making the VR headsets, and for them 3D is something very different. Then you have 360 cameras, that's also 3D. There's so many variants of 3D that just saying 3D foundation models is actually a little bit, it sounds like we kind of don't know even what it is, which is why we're coining it that way, because it's not well defined. So once we define it well, I think that's when we're going to see it. And if you look at current foundation models, I'm going to take language as a side, because language has different properties than vision. There's large language models already operate at a level of abstraction above and at the intelligent level of abstraction, which is language. Vision foundation models operate on natural raw signal. And if you look at what vision models are doing right now, they're very narrow scope. We have a foundation model for segmentation, very narrow scope of vision, of computer vision and perception. So I feel that we need to sort of ground ourselves and narrow a little bit what we want to solve. And then we can talk about how that's going to happen and what data. And if there's a company working in, I kind of doubt it, because this is too advanced and people in companies are not as competent as you think, so that they can actually solve these tasks. Oh, sorry, if there's company people here. Then they will actually do something that's very narrowly defined for a specific task so that there is an application.
What the interplay between like the vision, like the vision modeling, the foundation model and vision, and large language model?
Which foundation model and vision? There isn't a foundation model in vision.
Whatever you're defining right now, right? We're thinking about defining how that can be defined.
I think we need to have a specific task and like a very well defined.
It's not right, but the point that the question is, can the interplay between large language model and our thinking about what foundation models in vision could be inform better what we want to do in vision?
Yeah, sure, perhaps. I think that language is maybe I'm definitely not in the camp of some colleagues. I think that large language models solve all the problems like kinematics, control, and whatnot. I don't see that, but sure, if you figure out how to fuse multiple modalities where one modality is language, then yes. But I disagree with the term foundation model for vision, because I don't really know what that is.
Thank you.
Yeah.
I would say, I would say I agree. Like when you say like large language, but like large foundation model for 3D, I don't know what to relate it to, right? Like so, like closest I get to is, I don't know, these stable diffusion like big models, but then these are like text to image kind of things, right? So, and do we really want to be like, so there's a lot of work in this text to image kind of works, but I don't feel like text is the right modality to even like think about when you're creating content, right? Like how loosely defined is the concept of text, right? Like if you want to define how to edit a chair, as a designer, would I be better with having like knobs and like sliders, or am I better at like using these text based and trying to specify it somehow? So I don't clearly see what is a 3D foundation model, right? Like I can see like parts like, okay, are we talking about texturing as a thing? Are we talking about like generating like generative models for just generating objects of a specific category or whatever? But like not sure what a 3D foundation model is to be honest.
Sounds good. Yeah, definitely.
All right, so I would take the answer to say that a foundation model should be a model that is very large. And second, that is trained hopefully in a self-supervised, unsupervised manner. And then the SAM model already acknowledges itself as being an outlier in this regard, because it uses kind of labeled data. And so I am particularly interested in generative modeling. And so I would start with the idea, can we train object level generative model that is so powerful that almost any object shape we encounter in the real world would be in this model. So any of the chairs or tables or here would be kind of in the generative power of this particular model. And I think one of you mentioned the Observerse XL, you know, this is kind of maybe going in that direction. And I think that on the shape level is maybe something that can happen sooner than later. But at the material level, I feel this is quite challenging still. I don't know that we have a good enough database of all possible different materials, and we also need the lighting that we can get there. But I guess we'll see. But maybe for shape, more hopeful.
Thank you. You already answered some part. So let's have a last general questions, and then I would like the people who would like to ask questions to line up here for following up. So the last general question, which happen in every kind of panel discussion, is like, how would you predict your next 5 years in your domain? How would that look like? Please go ahead.
How would I predict my next 5 years?
Yes,
in my
your specific domain, so 3D data generation or
okay, first of all, I need to figure out my domain. That's one thing I do need to figure out, but I guess maybe I'm trying to do language and 3D. I do think, you know, there will be a lot of efforts to use cross-modal information to try to understand 3D. But I think that's maybe in the next year, maybe next, if I go to 5 years, I don't know, maybe we will have, I think there will be maybe a bit more focus on, like, once you have, let's say, assuming that you have made a lot of progress in like generating content, you can have something to, it's probably also be more focused on analysis and, like, you know, what can these models do, assuming you have some more powerful, I don't know, foundation models, the word, actually, I want to say one word about language models. The word language model is very specific. It means that it predicts the probability of a sentence. Okay, I don't know what a foundation model predicts, but so yeah, so yeah, so anyways, maybe we'll need to basically be able to figure out, you know, what is this good at, and I would like to personally move in this in the direction of this workshop, actually, compositionality, whether I can generate, you know, things that I have not previously seen.
Okay, so this is impossible to predict, but I will also make a guess. Okay, yeah, so I think graphics will be pretty solid. You'll be able to generate 3D assets very well, super photorealistic. VR will do super well, and etc. Now, so I don't work on that field, so I work on vision, and you know, it's slightly harder, but again, we're going to see insane progress. I think one progress that I expect we'll see is that instead of focusing on labeling objects and predicting masses and so on, we'll figure out, we'll do more better fine-grained perception, orientation of things and the state, etc. And simulated data for training the models will, you know, be more prevalent, like simulation not from human artists, but right from generative models plus human artists together. Yeah, the hard thing to predict is whether video understanding will be revolutionized as well in 5 years, but I would expect that yes. I mean, something that we worked, I mean, starting from Peter's answer in the previous question, he said large scale and handle every object. I would imagine one foundational model for 3D, for example, that we worked a lot in the past was view prediction. Like you have one view and predict the other view, and we've seen that the best way now to live 3D is you have an awesome view prediction model, and then you distill it in 3D. And actually, the other workshop, they had a lot of works in that direction. So the same way that we have some views, and then you have a relative pose and predict the other view. So that relative pose is, let's say, the action. Okay, so instead of just changing the camera, which is one type of action, you have other actions that, an end effector can do. So you have a foundational model of the forward. It's a foundational forward model of what can happen in the world. So I think predictive architectures will do very well. So we'll go from view prediction to any action condition prediction. So I would hope action recognition, fine-grained action recognition will also, have insane progress in the next 5 years.
Again, we're all answering?
Yes.
Okay. Okay, so I have to say something different. And I'm gonna go a step above, I think. And instead of sort of focusing what the specific problems will be, I think that what we all ought to think is, why are we doing what we're doing? Why are we solving what we're solving? And at the end of the day, I have a feeling that a lot of the research that I see at CVPR, and I'm saying that as a person that comes from a company, is that we're all working very hard at making Zuckerberg, Sundar, and whoever else very rich. And that's great. They are very thankful. There's 10,000 brilliant people in this conference all working in that direction. So I want to suggest that I think that it's great to think about 3D and the problem of object understanding VR, video understanding, great targeting for ads. You sell more shit to people, great. Zuckerberg's very happy. I think there's going to be a lot of revolution, in my view, in the scientific discovery domain. This is where 3D, if you look at where 3D is right now in use in doctors, in biology, in astronomy, it's very rudimentary. They are in need of our expertise and methods to make a lot of these tools used for not to make, presumably some pharma company will get rich along the way, but perhaps we're also going to be saving some lives through making some of these tools actually work and applicable. So instead of trying to generate shares, let's, cure some stuff.
Thank you.
Oh, sorry.
That's a really good answer. Yeah. So as a PhD student, yeah, I don't know, like if I look forward to like the medical domain more, but the money isn't like making Zuckerberg rich. So yeah, it's
the money for who? For you or for Zuckerberg?
Yeah. Right. So, but yeah, in terms of what's there for the next 5 years, yeah, it's pretty hard to predict. But like with like all the new products out there, right? Like the Oculus and like this Apple VR headset, and so I think a lot of the stuff we've been keeping in research is gonna come more frontline, and like people are gonna experience it. So I think we're gonna even discover some new use cases and like some problems that we were maybe not exposed to as researchers, like because like you see how much of the research was driven by like the artist community now. Once these 2D generative models got like popular, right? So I expect the same level of push from the consumer side in terms of research directions as well. Once these VR devices, AR devices get really popular, and this is something I'm kind of looking forward to. Yeah.
Well, so I'll just offer one observation that I guess everybody else made, is that the pace of research is just insane right now. And that, I'm really old here, but when we started out in graphics 20 years ago, you could read a paper and you could think about what you want to submit 1 year, 2 years from now. And these were all huge projects. You needed to, people didn't give you the code. You need to go 6 months, re-implement the previous paper. And I think what happened now is that through maybe a bit more sharing and really good infrastructure, the pace just increased to an insane level. And it is very difficult now to make like a 5-year research plan. I used to kind of be asked that in an interview, but I even for myself would say it is difficult to say what's what I want to achieve in 5 years. I would more say I have my core topics that I'm interested in, and I'll see how these topics kind of fit with how the field moves. I mean, one thing that I think can have the significant improvement that this 2-image generation has is maybe the 3D generation. Can we have tools for 3D object generation, for maybe even 3D scene generation that rival the current mid-journey success or other 2D diffusion models?
Okay, so I have been like thinking about in the space or working with vision and language in different ways. And but if we reflect that on, let's say, well, world scale problems, like how this can help. For example, if you want vision systems that can understand the, let's say, the 8 million species in our planet, and maybe we have capital of dome and we build systems that can recognize species that has not yet been discovered and explain how different they are from those that we have known. And hence, these kind of work can accelerate, let's say, behavioral ecology research. How this kind of system can understand how these creatures interact with the ecosystems above water, like the environment where we are, underwater, coral reefs, and how the marine species are behaving. And if this behavior is normal, is it in the expected space? Are they growing in the way that we think is the right thing? If we want to, if we really have a system that accelerates research in this space, we need systems that can understand the growth like that. I've interacted quite a bit with behavior ecologists in marine science, and they really care about the geometry of the corals and how does this change over time, and how this may make an implications in what decisions makers should do to protect the environment and help large problems like climate change. So this is some sort of problems. When I think about this foundationally from scientific perspective, I kind of try to think about maybe general. I relate that to general, what some people call general purpose vision models. And one way I think about it is by connecting it to what might be called vision language models. And the way I look at it in a way that can solve many tasks in a generalizable way. There are different viewpoints from that. Is to have a vision system that can process vision plus language and output vision plus language. This probably any task we work with vision, or most of the vast majority of it can be can be a subset of it. Right? So if you have a system that takes an input vision union language output vision union language. This is what if we restrict it to vision only. This segmentation. If you have vision plus language, output language, this can be visual question answer, right? If this is language plus language only and image visual, this is like text to image generation, right? So you can pretty much approach general purpose vision systems by having a system like this, and maybe this could be one way to think about what is a possible vision foundation.
Thank you very much for the exciting answers. And please come for your own questions. Any questions?
So there's been a lot of hype on industrial metaverses. And maybe following on like doing something useful. Like I come from Calgary, and for example, mining companies, they want to do things, warehouses and so forth. So something that comes to mind is they say they want to create a digital twin of an environment and then learn something in that environment and use potentially, are there thoughts on how we can use content creation to help in those cases? For example, I know a drones company that was looking at warehouse box counting. And then, well, they can't scan all their warehouses, it takes forever. There could be different sunlight. There could be boxes with different shapes and sizes, contorted boxes perhaps placed that are squeezed. So could we create realistic content that helps solve those sorts of industrial questions, I guess is my question.
So in NVIDIA, you can see in their website that of the simulator that you will see whole warehouses being simulated there. Have you seen those videos?
I have. So they have in Omniverse, they have like a warehouse asset creator and things like that. But it's very particular to NVIDIA right now, what they have as available assets.
So basically what you want is you want to have a very accurate mapping of an existing warehouse, but in a simulated world.
Exactly. And then creating lots of variants of that, perhaps, of that particular warehouse. So I go scan a particular warehouse, and then I really like the idea of parts, and then parts can get bigger and smaller. So then if I have that particular warehouse, I can then create potentially boxes that are bigger or smaller, or different aisles, shading, things like this is not my key area. So I'm just posing the question as how do you see content creation helping in that direction? Is it easy?
Yeah, so I think this is one of, if you allow me to just say one sentence, I think this is one of the most exciting things of the last few months, that simulation creation was such a lot of money type of process where you had to hire so many artists, but this is being democratized now with those generative models. And right now it's on the object level. Anybody can download the code and put an image and get the 3D of it, or take two views of its objects and get the 3D of it. But this is going to move, I would hope, to the scene level and hopefully to the warehouse. The same way with augmentation of the current assets, as you say, to change the box and so on. Now, I don't know in what detail the box needs to be articulated and so on. It's simulated, but this makes a huge difference whether it just need a dead box or it needs to also open and close in realistic ways. But I would say for rigid type of asset creation in scenes, this probably is in a close future.
Great.
Regarding compositionality, it seems like it's a capability that we hope our representations will capture to deal with some complexity in the world. What in your minds are a good way to start assessing such capabilities? Currently, it seems like the way we assess it is we take an object we know and we see if it's going to compose it into parts, or we have a set of attributes and we see if it can do that. But it seems like if we want it to be composed, it needs to go beyond that in a way where we're actually assessing the representation itself rather than the behavior of the model that we're assessing. So I'm curious what your thoughts are on that, or if maybe there's another way to think about compositionality when it comes to representations, capabilities of models that we're training specifically to perceive things or to understand what they see.
Maybe I can try to answer is, I think that compositionality as a lonely property doesn't make any sense. What you want is you want a task that will allow you to do something through perhaps compositionality because you think that this is the right approach in tackling this problem. So at the end, you want to evaluate what is the end goal of what you're trying to do. So that is your task. And this in compositionality is a tool rather than the end goal. Yeah.
Okay, I say a few words. I agree with that sentiment, but if you did want to say, is your representation compositional in some way, if you have a predefined way, for instance, if you wanted to know that does it know something about attributes, does it know something about, how is it going to move, then you can potentially have probes that, test for that specific quality that you're looking for. That's not really actually tackling compositionality, but more about whether it's doing this decomposition so that maybe in the future can be recomposed. I don't know if that helps.
So I guess the answer, if you're assessing a model that you hope can do general perception, the idea would be to aggregate as many properties or as many tasks as well and check if it can decompose those.
I guess I would agree with Georgia in the sense that you want a specific task, maybe not necessarily so. But if you feel that there are certain properties that are useful for many tasks, then you can potentially assess that.
Thank you.
Yeah, and to mention, there are also some papers that exactly study this problem. How do we evaluate compositionality? And they say, you know, just make tests that are progressively more and more further away than the training set. Okay, in different ways. They say either add more objects or, you know, vary, let's say, the chair, but do not vary a lot the scenes to see if you can indeed do well on novel scenes and so on. So basically, you create tests that are further and further away than the training set to see in what amount your model can generalize to them.
Yeah, I guess like in those cases, it seems it's almost domain specific. And my thought is like when we talk about compositionality in humans, it seems like what we're getting at is that this compositionality allows us to go beyond tasks. Like sorry, across tasks, where you know how to compose this object, but then if you start thinking about a very complex problem, you can decompose it in a similar way, and you know, ideas of spatial metaphors and analogies, etc. And it seems like all our evaluations are still very focused on a specific task, which is great. But I'm curious if there's a way to go beyond that to abstract it away. But I guess maybe it's to remain focused on the specific task.
I think one way it is a very general question. Compositionality is quite broad. But one way to think about is think about, let's say, fine-grained species, right? They are composed of concepts, right? Parts or let's say birds, for example, they have beaks, heads, and things like that. But this doesn't mean that there exist some species that we know nothing about, right? So and they are composed of concepts that we do know. Right? But that particular configuration of let's say parts and features, either geometric or appearance, that entire composition that maybe has not been seen may define that this is a new species or not. Depending on after we, for example, of course, consult subject matter experts, right? But that particular that's, for example, one setting where we can think of it's a composition in this case of parts and attributes to define a new species. And in this case, thank you.
Thank you so much, by the way. I really enjoyed the panel discussion. My question is about the 3D compositional vision task. I wonder, how do you see, or what do you think as is a helpful application of it, or things that might already happen as a helpful application? I know we mentioned things like medical device or the robot movement, right? But what do you feel personally will be helpful as an application? Anything that you like.
One great work from NVIDIA last year was like very much associated with this asset generation task, right? Like once you think of these, I take an example of a chair as a composition of parts, the kind of objects you can go from there as a designer, like, okay, I just want the backrest to be longer, or the chair to have more legs, now to have wheels. You can specifically talk about the parts and what you want to change, and then this opens up naturally what kind of different generations you would have. So like compositionality in this aspect, like just opens up the more natural way on how you want to generate things.
Thank you so much. Anyone else has any favorite?
I mean, the standard tasks of detection, object detection, parsing, segmentation, part orientation, prediction. The more compositional you are, the better you will generalize, right, to different scenes.
Yes.
And then you will do also better to long tail classes, like in the long tails that you don't have a lot of examples, like few shot.
Thank you very much.
Maybe also just to add, like, when we think of a lot of like object generation works, like they just go like one shot, right? Like they're usually not doing like part by part composition and then generating objects. There are works, but like usually you see them just like doing like object as a whole, but not as parts. But once you start going to scenes, that you have to think about like compositionality. At least in the current works, it doesn't quite work as nicely. Like, so we do have these nice object-centered models, and then you can think of the scene as a graph or whatever, and then specifically generate certain objects on the one. So you're doing composition on a different scale now, right? Like the objects are like a room is composed of certain objects, but these objects are just generated on one. So that's one way to visualize that.
Thank you so much. Appreciate it.
So I have to apologize, I have to run, so thank you all so much for your wonderful discussion.
Any other questions? Yes, so thank you very much for the great talks and presentation and announcement and then for your time.
And thanks for organizing.